Am I sharing my screen or at the moment?
Yes, you can try to share. We still have 8 minutes to the beginning.
Okay, sure. Okay. In that case.
We have already 20 participants.
Great. Hello?
Hello.
Okay. I think there was some problem with the internet connection from my side.
No, everything looks okay.
Okay, good. Maybe I can just...
You can try to share your screen. I will stop my video.
Okay. Just a second. Does it work?
Yes.
Okay, great. Should we start?
Yes, we can. We already have 50 participants, so we can start.
Okay, great. So welcome everyone to the lecture on multi-agent reinforcement learning. I'm Goran Radanović. I'm a research group leader at Max Planck Institute for Software Systems, where I lead the multi-agent systems group. So naturally, my research interests lie within this area of multi-agent systems. I should mention that for my PhD, I was actually working on slightly different topics than what I'm going to present today, mostly related to incentive mechanism design. But during my postdoc, a couple of years ago, I got introduced into this wonderful field of multi-agent RL. So I hope I'll do justice when presenting this topic. So let me just briefly mention how I got to work on this topic. So as I mentioned a couple of years ago, I was working on an interesting project called Helper AI. And this project was about human AI collaboration in setting where decision-making procedure was lasting for a longer periods of time. You can imagine settings such as self-driving cars or assistive decision-making systems that help humans reach decisions. So this was sort of an overall setting, which I'm going to talk about more in the next part of the lecture. But interestingly, during that period, I came across a paper from Licklider that was published around 1950s. In this paper, Licklider gave a vision. They gave his vision of what an AI is going to be about, what the whole field of AI is going to be about. And this was somewhat different than what you typically see in, let's say, Hollywood movies that romanticize Minsky's vision of AI dominance. So Licklider proposed that what we're actually going to experience in the decades that follow from that year would be some kind of symbiosis between man and computer. So you would have sort of a joint decision making rather than one agent or one system dominating another. So yeah, naturally the system belongs to multi-agent setting because you have at least two decision makers, AI and a human. And we'll talk about this in more detail in the next part of the talk. But I just wanted to give you my motivation for studying studying this field. So what is multi-agent RL? I would say in the most, as the simplest explanation, I would provide that it's sort of a combination of multi-agent systems and reinforcement learning, right? So you're trying to study reinforcement learning framework and how to apply it in the scenarios where you have multiple agents. So naturally, we are going to decompose this lecture in 3 parts. In part 1, we're going to sort of introduce the notion of agents, basically from an AI perspective. Probably most of you have heard about this part of the lecture. You'll probably be familiar with what I'm going to talk about, but I think it's sort of nice to introduce a template that I'm going to utilize later on to explain concepts related to reinforcement learning. Then in the second part of this lecture, we are going to talk about reinforcement learning, basically from an introductory point of view. So basically the second part will introduce some of the basic concepts related to reinforcement learning and some of the basic techniques in reinforcement learning. And this part will basically serve us to put us on the same page regarding what reinforcement learning is about. And then in the second part of the lecture, we are going to focus on multi-agent reinforcement learning. And you can think of this second part as a part where we are basically applying reinforcement learning to a multi-agent setting. But as you will see, we are going to discuss some of the critical differences of why single agent reinforcement learning cannot be always trivially extended to multi-agent settings. Okay, so let's start with the part 1. So in this part, I really want to sort of focus on sort of an AI perspective of this problem, of the field of multi-agent interaction. So before doing that, right, it's natural to ask, how do we actually measure intelligence? This is something that we typically do when we start talking about AI in the introductory courses, right? We ask ourselves, what is actually intelligence? How would we actually recognize that some system is an intelligent system? So I'm going to propose 3 possible definitions that were present in the literature. So probably one of the earliest definitions goes back to Turing in his famous paper on imitation game. So in this imitation game, you basically have 3 agents. 2 of them are human and 1 of them is AI. And the goal is that this human agent, inspector, the goal for the inspector agent is to guess which agent they are interacting with. So the inspector can actually communicate with both AI agent and human, but it doesn't see which agent is which. So these 2 agents are actually placed in 2 different rooms. The inspector doesn't see them. It can only interact with them through a series of questions, right? And the goal for the inspector is to guess which agent is which. And if you think about it, this is kind of a really natural way of defining or measuring whether we achieved intelligence, basically whether we achieved a system that behaves intelligently. The reason for this is very simple. So when we say something is intelligence, we have to have some kind of a reference point, and the most sensible reference point is another human agent. So if we can't distinguish between a human agent and an AI agent, we could say, you know, an AI agent is at least as intelligent as the human agent, right? So one way of measuring intelligence would be through this Turing test. Now, of course, this Turing test is not actually very practical because, first of all, it's not easy to fully imitate human, right? And secondly, it's not even clear that we should, put human as a reference point when we are talking about intelligence. So typically, in practice, what we resort to is a definition that tries to measure intelligence through some objective, or through objective function which quantifies how well our system is behaving. Right. So the second definition of intelligence, or the second way of measuring intelligence, would be to say that, you know, a system is intelligent if it behaves rationally, and rationally here meaning that it maximizes utility. So, for example, if you take a look at this figure on the right-hand side, we would say that a system is intelligent if it takes this trajectory tau2, because this trajectory, first of all, reaches the goal from the start state, right? If you have two points A and B, and we want to reach B from A, then we would say that the intelligent way of reaching B would be through this trajectory tau2, simply because, first of all, this trajectory reaches the goal, and second of all, it also reaches it in somehow a near optimal way. Okay, so that sounds quite nice, but somehow we are limited to a particular task at hand, right? So maybe a third way of thinking about intelligence would be to think of it as from a point of view of multiple tasks at hand, right? So we could, for example, say that a system is intelligent if it can achieve goal in a wider range of environments. And, you know, basically we are trying to do something that humans typically can't do. So, for example, we could try to ask an intelligent system to solve the task on the previous slide. So basically finding the optimal path from point A to point B, but at the same time, we could require from the system that it knows how to drive cars, or that it can play Atari games. This definition is basically outlined. I think it actually goes back to Hatter, who tried to even formalize it using Kolmogorov complexity. Now, Kolmogorov complexity is not computable, right? So you might say that their formalism is not very practical. But I think it still gives an interesting insight into what we want to do with intelligent systems. Of course, we also have to have in mind that the notion of wide range of environments is not, I would say at this point, properly defined, because we know that due to the no-free lunch theorem, this wider notion has to have some limitation, right? There is no system that can behave well across all the domains, right? So it has to be somehow, the definition has to be somehow restricted. It has to be somewhat more properly defined. Okay, so maybe we can start with the second perspective on AI and investigate what rational agents are about, right? So the way we would formalize this would be to say that there is some environment, and this, and that we also have an agent, and this agent interacts with the environment. First of all, it perceives it, so it somehow senses the state of the environment, right, through either visual sensors or audio sensors. And once we have information about the state, we process this information, and we make actions in the world, right? So this is what an agent would do. How we would like our rational agent to behave? Well, we would like it to map these sensors into actions, but map it in a way that we optimally achieve our goal, right? So in one of the examples from the previous slide, we would like to reach point B from point A in an optimal way. So yeah, so we would like to reach the goal and also reach it in a cost-efficient way, so to speak. Now, this is nice, but it's a really high-level picture of the world, right? We need some more concrete formalization. And in reinforcement learning, a suitable framework to start reasoning about this formalism is based on Markov decision processes. So what are Markov decision processes? Markov decision processes are basically stochastic processes in which an agent describes the world through states. So environment at time step t is in a current is in some state st, which is sort of like a random variable, right? And then an agent observes the state. And for the most of the lecture, we're going to assume that this agent fully observes the state, meaning that it has all the information about the environment according to which it can act. Once the agent observes a state, it acts according to its policy. I'm going to talk a little bit more about what this policy actually does, but from this policy and the state of the environment, we can derive agent's actions, and agent's actions here are denoted by AT. Agent's policy is denoted by pi. So these actions have effect on the environment, meaning that the environment updates its state from state st to st plus 1, and it updates its state based on the action taken by the agent, AT. And the updating process is basically sampling process. We sample a new state from some probability distribution that depends on state of the environment and the action of the agent. Okay, but before we change the state, we also give the environment also gives some reward to an agent, depending on the current state of the environment and the action taken by the agent. So reward is basically a function of the state and the actions. And now, of course, there are different ways to actually deviate from exactly this description of Markov decision process, but I'm not going to go into too many details. Basically, we are going to try to follow this framework as stated on the slide. What would be the goal here? The goal would be to find a good policy pi. Okay. So maybe at this point, I can just check if there are any questions on Slido. Yeah, please feel free to ask any questions. I'll from time to time check them and try to answer as many of them as possible. So goal is to find the good policy. Good policy here is basically described, the goodness of the policy is described by the reward function. I'm going to talk about this in the next few slides. Okay, but before I talk about it, let me just try to provide you with some simple example of MDP environment. So this example goes back to our paper and that I'm gonna explain in the next lecture. But I'm just going to simplify here a description by saying that, you know, we are trying to investigate, we are trying to describe a really simple setting in which we have a car that is driving on a road from starting state A to destination state B. So the goal is to reach state B from starting state A. And to do this, the car needs to traverse intermediate states Cij. And there is also an accident state D in which an agent can end up if it makes errors or purely by accident. So we have states A, B, C, D, and these intermediate states that are basically denoting positions. Actions that an agent can take in this simple environment is either to go forward or to go forward and left or to go forward and right. So there are basically three actions. So state space is described by A, B, C, D, C, I, J. Actions set is described by left, right, forward. And then we also have transitions and rewards. Transitions are telling us basically the position of this car is changing as we take actions. So if you, for example, take action left from state C33, so basically from the middle of the road, we are going to end up in this state. So that would be state C44 with really high probability, 99%, but there is some chance that we end up in an accident state D, right? So the world is probabilistic. And finally, we also need to define what the reward function is. For example, We want to minimize the amount of time that this car spends on the road. So rewards are actually all the rewards are actually going to be negative here. If we are in middle of the road and we just take turn left, then maybe the cost of turning left is relatively small because we are doing a safe action. But if you are in a state C5-1, let's say somewhere here, and we are turning left, then we might end up in the accident state, and this is highly costly for us. Okay, so what do Markov decision processes describe? So as practical examples that that we can mention that highly relate to reinforcement learning are basically robot control. So I mentioned here 2 robot control examples. One of them is controlling quadrupedal robot, and we are going to talk about this later on. Another one is from Eng et al., where we are trying to find a good policy for a helicopter to perform different maneuvers, such as the one where we sort of put a helicopter upside down. Another example would be games such as Atari games. We are also going to talk about this example later on, hopefully, if we have time. And finally, additional example could be educational games, such as the one presented by Mendel et al., where the environment itself is a human agent. So the goal of these educational environments is to somehow find a good educational material there is good curriculum for a person that is trying to learn something. And maybe you have already seen some examples of this in your machine teaching class. But basically, what we want to do here is evaluate different types of policies based on data that we already have in order to deploy a new policy that would maximize the learning performance of the learner itself being an environment. Good. Okay, so these would be just some practical examples of where we could, in which we could use MDP to describe as a model of the world, and then we could apply reinforcement learning on top of it to find good policies. Now, what we haven't talked about at this point is how to actually, what the policy actually is, how to represent it. So typically we consider 2 types of policies. These policies can be either deterministic, meaning that policies function that map states to actions, or we can have stochastic policies, meaning that we randomize over actions. So stochastic policies are obviously more general than deterministic policies. So here, stochastic policy would randomly select a certain action in each state S. Okay. Secondly, we also need to say something about how we actually represent these policies. So the simplest possible way would be some kind of a tabular way, which is often suitable for, let's say, deterministic policies, and we should literally specify for each possible action, for each possible state, what the executed action would be. This is often inconvenient for large state spaces, as we'll see later on. So an alternative way, which is often used nowadays in deep reinforcement learning, is to specify policy pi using parameters that are defined by deep neural network. So a deep neural network here would be a mapping of state. So deep neural network would have as an input a state of the world, and it would output, say, probability distribution over actions. For example, this last layer, if you are talking about discrete actions, would be a softmax layer. And the softmax layer would basically, by sampling from this neural network, we would basically effectively be able to sample from a policy parameterized by parameters of a deep neural network. Okay, secondly, we also need to define what our objective is. Right? There might be different objective functions, but one that is typically considered in reinforcement learning is maximization of a long-term total reward. So let's maybe briefly go through it. So what we have here is maximization objective in which we want to find a good policy pi. And we are trying to find an expected value because the world is, stochastic potentially. Expected value of the return. So the sum here is nothing else but the return of an agent. And this return is quantified from the starting state S1 by executing policy pi. And of course, we need to, in this expectation, include also uncertainties in the environment. So we need the model of the environment to calculate this expectation. What is the return here? The return is basically nothing else but a cumulative discounted reward, starting from t equal 1 to some horizon h. And basically, we are summing up the rewards. And these rewards are discounted by gamma factor. Gamma here, discounted by gamma factor, which is always between 0 and 1. And in the case when gamma is 0, we're just optimizing myopically. In the case when gamma is 1, then, well, we are equally treating all the rewards, but typically this gamma is between 0 and 1. And this basically means that we favor rewards that are obtained earlier on in the decision-making procedure more. And sometimes, as you will see, we will set this horizon to infinity. If we set it to infinity, this sum is still well defined because we have a discounted factor that decreases geometrically as we increase the time steps. Okay, so let me just check if there are any questions at this point. Okay, there are no questions, so we can proceed. So in the first part of the lecture, we are going to discuss 3 approaches of how we can optimize this objective. So that is how we can find a good policy. And these 3 approaches will basically follow the template that I described initially in the lecture. So the template that used these 3 different views on artificial intelligence and how to measure artificial intelligence. So first, we are going to say something about how we can imitate an expert. So assuming that we have data collected from human expert, we are going to ask a question of how we can then design a good policy solely by looking at the expert data. Then in the second part, we are going to talk about planning procedures. So assuming that we have a model of the environment, we're going to ask whether we can derive good policies by using basically planning under uncertainties in this Markov decision process framework. So these methods will require exact models. So in the third part of this lecture, we are going to talk about model-free reinforcement learning, where we don't have access to the model, and where we want to also scale up, meaning that our state space can be, for example, described by images. This typically is not easy to achieve with the methods described in the second part of that we are going to describe in the second part of the lecture. And the third part of the lecture is basically something that when we think of reinforcement learning, this is something that we typically think of as a methodology for reinforcement learning. Okay, so maybe Let me check if there's anything on the slide though. No. Good. Okay, so let's then start with the first part of the lecture, which describes a system that imitates human behavior well. So one of the simplest methods along this direction is behavior cloning. So behavior cloning is an imitation learning approach, which assumes that we have high quality demonstrations data that are coming from one or more experts. And so first of all, why would this be useful? Well, this would be useful in cases where it's actually not that easy to describe the reward function in Markov decision processes. For example, in driving scenarios, it's often easier to just provide demonstrations than to actually specify what exactly the reward is. Okay, so now the question is, if you don't have reward, but you have demonstration data, what do we do? So in behavior cloning, we basically just do supervised learning. So we try to minimize a certain loss function that, of course, depends on the policy, but it also depends on the demonstration data. And our data point here is basically a state action pair. So the state action pairs can be sort of effectively retrieved from the trajectories. And remember, the state action pairs are basically telling us how an expert acted in state S, and they're basically saying that in state S, expert did action A. So what we are effectively doing here, we are basically trying to match the behavior of an expert, right? By minimizing this objective, okay? And if you think of policy as a mapping from states to distribution of actions, this is effectively a prediction task, right? Because pi of S here is nothing else but probability distribution over actions. And we are trying to match pi of S to what human would do, which means that you are basically trying to predict with this policy what human expert would actually do. Okay. So this is a classical supervised learning approach. We know how to do it. It's really simple and efficient. When it works, it's great. The problem is that it actually ignores covariance shift, right? So we are optimizing here an objective that effectively assumes that we are going to use at the execution time a policy that human is using. And this would be fine if we find the perfect, if we find a pi that is perfectly imitating human behavior, but we are never actually, we are typically not finding that, right? So the distribution of state action pairs in this data set is not actually going to be the same as what we are going to experience at the execution level, right? So that's one problem. And another problem is that this method doesn't plan ahead, right? It just tries to mimic myopically what a human would do, right? So you sample a point and you try to mimic what human do at certain state. And yeah, so basically what you can think of behavior cloning by saying, you know, what we are trying to do effectively here is we're trying to match or a match policy of a human by assuming that we have sort of executed perfectly, by assuming that we imitated perfectly human up until that state, right? So does this work? Well, sometimes it works quite okay. So I'm going to show you here a video from Kodevilla et al. Let me mute the video, which explored how the performance of behavior cloning in a driving simulator. What you can see here is that behavioral cloning is performing quite okay for most of the time, but there are periods where it makes mistakes, and these mistakes are often made because of the bias in the data set, meaning that humans, know how to drive, and then you don't often see in a data set rare events. So you don't actually know what to do when as an algorithm, as a behavioral cloning policy, you end up in a state which was not visited by human. And there are also some effects that are related to causality. For example, if a car stops, then it often stops for a longer period of time, not recognizing that it can initiate in driving after that. Okay, so let me just illustrate this drawback of behavior cloning pictorially. So what is actually the problem here? The problem is a problem that is known to often be the case in some of the critical environments. And this is the problem with compounding error. So suppose that your agent behavior cloning starts in state S1 and executes the same action as expert. This would then lead them both lead the behavior cloning agent to state S2. Right, and in the state S2, we know what expert would do because, for example, we have a data point for that state, right? But because behavioral cloning agent is not a perfect agent, it makes a mistake, and instead of executing what expert executes, it ends up executing something else, and it ends up being in the state S3 prime, which is different from what you would which is different to the state than where you get if you execute what expert actually would do. And here is the problem. If for the state S3 prime you don't have a data point, you don't actually know how to behave, right? So behavior cloning agent in this case would maybe take completely different action than what expert would typically take and end up in a catastrophic state S4. So basically, this happens, because effectively behavior cloning agent doesn't account for the fact that at testing time, your distribution of state action pairs is not the same as the one during training time. However, behavior cloning works quite well if you have sufficient data, basically data that covers state space. So there are also other techniques to behavior cloning, to imitation learning, sorry, that basically try to alleviate this problem. One of them is based on interactive imitation learning, where we are interacting with the expert and querying expert whenever we don't know what to do in the states that expert haven't visited. So this, however, requires a lot of interaction with experts in domains where you have quite stochastic transition dynamics. Alternative approach to this would be maybe to try to infer the goals of what expert would do. So if you remember, one of the reasons for utilizing imitation learning was because it was sometimes hard to figure out what the true reward function is, to specify true reward function. So maybe instead of directly acting on a data set, what we can do is we can first try to learn what the reward of the human demonstrator is, and then utilize reinforcement learning. And this is exactly what inverse reinforcement learning does. Okay, we are not going to go into details about these interesting imitation learning methods, but feel free to ask questions. I'm happy to answer. I should also mention that imitation learning is not only useful for providing us with good final policy, but it's also useful for initializing prior policy, and this we will see in the next talk when we discuss some of the multi-agent reinforcement learning algorithms. Okay, so this concludes the first part of the lecture. Let me see if there are any questions at the moment. Okay. So there is a question. If the expert knows what the actions to do in a certain state, why don't, I guess, we simply program the policy according to that instead of loss function? So that's a great question. So yeah, if you can do that, that's definitely one way to go about the problem. But in domains such as, let's say, robotics, it's not actually easy to specify exactly what one should do in each possible state, because you simply have too many states. For example, if you have a continuous space such as in robotics, this is really hard to do, because you will need to really specify for each possible state what the algorithm would do. Similarly, for car driving, well, you could use rule-based systems. They are quite practical, but I guess you would need to specify how the agent should behave in every possible situation. This is simply sometimes infeasible. Good. Second question, can you combine different optimization methods, like get data from an expert to give learning head start? Yes, this is exactly what I meant by the previous slide. So imitation learning can actually be quite useful for designing prior policies. You'll see in the next lecture that some of these advanced reinforcement learning techniques are actually doing exactly that. Okay, there are also some questions about multi-agent approaches, so I'm just going to defer answering these for the next lecture. You told that there's a problem in supervised learning with a bias. What do you mean by that? Because of the next slide, it was told the lack of generalization are still open problems, and that means that you should increase your bias and avoid overfitting the learning data. So what I meant by bias basically is the lack of data for certain states. So if you go back to this slide, so as you can see here, behavior cloning agents did a mistake in one state, let's say state S2, and ended up in state S3. And in this state, we don't have any data about what experts would do. So basically, behavior cloning agent is just guessing what to do in that state. And what I meant by bias here is that if your human agent is performing well, it rarely encounters situations of rare events. Right, so your behavior cloning agent doesn't know what to do in these situations. Okay. Let me maybe answer a couple of more. Is there a potential problem with inverse reinforcement learning that agents learn initial policy? It will not learn some much better unexpected behavior for humans. Sorry, there, okay. So that's a good question. I think the goal in reinforcement learning is to actually figure out the exact reward function of that the human is trying to optimize. Of course, if you guess it wrongly, so if the reward function that you learn is not correct, then you might not be able to achieve the same optimality as a human agent. But if you do infer it, if you, in ideal situation, infer this properly, then you can actually even outperform your expert. And this is sometimes happening in some of these situations. So even if your expert data is not optimal, by learning the reward and then optimizing over it using reinforcement learning, you can actually outperform human. But it's also the case that by outperforming human, sometimes your goal is not to outperform humans, as we are going to see in the next lecture, but actually faithfully mimic them. Okay, let me see a couple more. If you have several states, as you are saying, how can you compute the loss in the states? You don't have ground truth from the expert then. So let me see if I understand the question. So if you compute the loss in the states you don't have the ground rule, so you can do that, right? If you, that's the whole problem, right? This loss function is basically you're minimizing this loss function over the data set that you have. So if you don't have data for some points, you can't. I mean, your performance won't be as good as you might want it to be, simply because I mean, statistically you should converge, and you are converging as the data set grows larger and larger. You are converging to optimal to performance that an expert is giving you, but because this data set has fixed size, there are simply problems that related to policy pi not perfectly imitating expert, and then this distribution actually changes, right, at the execution time. So you're not actually seeing some states. You're actually seeing states that are not present in the data. Okay. How to evaluate if we have enough data for behavioral cloning? Well, you can try to design performance metrics, right? Basically, you can see whether the system works at test time, right? For example, if you are talking about imitating a behavior in, let's say, Atari games, you know the score that an expert typically reaches, and you can compare this score to what behavioral cloning does. If you are talking about, I don't know, robotic systems, well, you can see once you test the system, you can see whether the system is working properly or not. But you can basically test it in reality. What's the relation between genetic algorithms and reinforcement learning? Well, genetic algorithms are basically optimization technique, whereas I would say reinforcement learning is a framework for learning the optimal policy. It can use, I would say, evolutionary techniques, as I may indicate later in the lecture. But yeah, I guess you can apply some of the evolutionary strategies to obtain reinforcement learning algorithms. Yeah, so reinforcement learning is basically a framework. It's a framework of learning the control, how to control an agent. Okay, this I'm gonna answer the question related to multi-agent approaches later on. Maybe I can also, yeah, let's leave it for later on. How to work with the state space if it's uncountable, and are there some constraints that are put on a reward function? So yeah, you can work with uncountable state space. We are going to talk about this more in the third part of the lecture. Basically, you can have continuous state spaces, in which case your policy should be, for example, a neural network that takes such a state space as an input. For example, you can take as an input velocity and position of an agent, and this is uncountable state space. Good. Okay, and yeah, that's it for now. So let's maybe continue with the second part. Okay, so yeah, so for now, we have talked about learning from demonstrations. An alternative to learning from demonstrations is to achieve a supervision using reward functions. And sometimes this is really easy to specify. Sometimes you really know what your goal is. In games, for example, the goal is to maximize score. And let's say sometimes in robotics, the goal is to reach a certain point with your, let's say, robotic arm. So in the next, in what follows, what we are going to discuss is how to basically do planning under uncertainty when we know the model. So let's go back to our objective function. Our objective function is, as I mentioned, maximize the total discounted return. starting from state S1 and executing policy pi. Okay, so basically this expectation here is, as I mentioned, the total discounted return from state S1, assuming that we follow policy pi. And it's actually defining what we call value of a state S1, right? And we can actually generalize this concept. So we don't need to necessarily define value only for a starting state. We can do this for all other states as well. So basically what I mean by this is we're going to try to evaluate each state by the return that we achieve with our policy pi. Basically, we are going to try to evaluate this expectation for each possible state. So more formally, we're going to define a value function that is that is dependent on a state. And this value function will output the return that we would obtain, assuming that we start from the state that is given in the argument of this value function. So this is basically rewriting what we have in basically generalizing our objective in a way that we introduce additional mathematical logic. Okay, and furthermore, we can even generalize the value function itself by defining something that is called state action value function, which now says that we're not only going to be able to define. We're not only investigating the return from different starting states, but we are also able to intervene on the first action, right? So Q values here are denoting the return that one obtains by starting from state S, executing action A, and then following policy pi onwards, right? So the point here is that you are able to intervene on your first action. The rest is basically the same as what we had in the value function. Okay, so how do we actually obtain a value function for a policy pi? So what we want to first do is rewrite this big expectation here. Sorry, this screen is really not convenient. Can I somehow minimize? I can actually minimize it. Good. Okay, so what we want to do is rewrite this big equation in a way that will allow us to somehow conveniently apply computational methods, right? So what do we do? So what we can do here is pull out of this expectation the first reward, right? Because the first reward is nothing else but the reward of the state. It's dependent on the current state and the policy that we are executing. And for simplicity, I'm going to assume here that we are dealing only with deterministic policies, right? So we can pull this out of the expectation. And then the rest, that the remaining part of the expectation is nothing else but the value of the next state. So you can rewrite it in this way, this equation here. And the only problem is that we don't know what the next state is for our policy because the world is stochastic, right? Okay, so we need to average over possible next states. And this is exactly what the second term in this equation is telling us. So what we obtain here by extracting the first reward is the first reward plus discount factor times the average value of the next state. And the average here obtained by averaging over possible next states. And the way to average this is basically to average the values of the next states, which is done by this equation, right? So you go through all possible next states and you multiply the value of their value with the probability of reaching that next state. Okay, so it's really that simple. Okay, so how does this help us? Well, if you go back to this, it helps us because now we have a system of linear equations. The unknowns here are basically values of states. We don't know them, but we have this equation holds for all possible states. And the only thing that we don't know in these equations are values of states. So we can just try to solve these linear equations. And there are different ways of doing this. But one that is quite practical is called policy evaluation. So policy evaluation basically tries to evaluate policy pi by using Bellman equation. And it's nothing else but dynamic programming approach to solving this evaluation procedure. So what do? Well, we initialize a value function to some values. Let's say we put all the values to 0. And then we repeat this process until we converge. We repeat the following process. So we basically utilize the previous equation. So this equation is given by saying that y pi of s is given is equal to something that we know plus gamma times some weights times something that we don't know. So what we are going to do now is basically iteratively update left-hand side part with the right-hand side part that we previously initialized. And this is exactly what policy evaluation is doing, right? We are just calculating new values from the old estimates by using the Bellman update rule, the Bellman equation from the previous slide. Okay, and it turns out that this, by doing this, you can actually calculate values, meaning that you are going to converge eventually. So we just need to repeat this process until we converge to values in which vk pi of s is not that much different from vk minus 1 pi of s. Okay. So this is nice, but what do we do with values of the policy? Well, we can optimize, right? We can start with some policy pi 0, and then iterate until we converge. And we iterate the following two steps. We first calculate the quality of the first policy, meaning that we calculate its value function. Okay. And once we calculate its value function, we decide how to make improvements over this policy. Okay. But the first step is basically policy evaluation, the algorithm that I showed on the previous slide. And then what we do is the following. So we go through all possible states and we update policy by setting it to action that maximizes this equation. Okay. Now, what happens if we put a in this equation equal to pi k of s? Well, if we put it to pi k of s, we are going to obtain by Bellman update rule v k pi of s, right? So by Bellman update rule, we know that we know what the value of this will be for actions that are coming from policy pi of k, right? Because we have this relationship. But we can actually also improve on this. And if you take a closer look at this, you're actually going to discover that this is nothing else but a q s of a, q pi k s of a. So effectively what this policy improvement is doing is it's analyzing q values, q pi k values, and it's trying to select an action that gives us the highest q value. So in a sense, it's really greedy approach. It's greedy approach with respect to the q values. Okay, so this is sort of just some intuitive explanation of how the policy iteration works. But what's really important here is that policy iteration is guaranteed to converge. So this greedy approach is actually guaranteed to converge to optimal policy. And in addition to this, it gives us optimal value function. Now, of course, there are other ways of doing this, such as value iteration and Q value iteration. We are not going to go through them, and they're quite similar to what I just explained. So maybe I can see if there are any questions at this point. Let's see. Okay, there are no questions. So I can proceed. Okay, so basically, right, so the policy iteration is this really nice procedure, which is really simple to implement. It's basically just dynamic programming. But it has limitations. The limitation is that in order to solve policy evaluation, in order to make it work, we required two objects. We required rewards and transition models, because this is what Bellman equation is telling us that we should have. So basically, in other words, we assume access to the model of the environment. That's the first limitation. The second limitation is that we were often iterating in the procedure over the state space, right? And also over the actions, because we were optimizing in each state. We were trying to find an action that maximizes the Q value, right? This means that we effectively assume, for all practical purposes, that state space and action spaces, states and action spaces are relatively small, meaning that the model is relatively small. So if you want to do planning in this way, we need to somehow constrain ourselves to models that are not too complicated. Good. So what if rewards and transition probabilities are not known? Basically, what if the model is not known? Where we are not completely in a hopeless situation, because we are interacting with the environment, right? At each time step, we are obtaining, state. We decide on action. We also obtain reward, and we also obtain in the next time step. We also obtain the next state, right? So we can draw some connections here, right? We learn about the rewards function, and we also learn about dynamics by knowing how the state is evolving over time, right? So the idea here would be to learn from experience, right? Learn from the data that we obtain by interacting with the environment. Good. What about large state spaces? I think there was this question some time ago, right? What if you have continuous space, or what if you have discrete space, but it's kind of like really big? An example of which would be, for example, Atari games. So here we have Space Invaders, where the inputs, where the state space is defined by images that are coming from game. So how do we deal with this? Well, remember what I mentioned. Policy can be parameterized. So we are the one who are deciding on how to parameterize it with respect to input. And that's fine. But still, in policy iteration, we are requiring value function. So there is no reason why we won't do the same thing for value function, right? So we can parameterize the value function in a similar way, right? We can define a neural network that tries to map the states into the value of that state. So for each state, it tries to map the image of that state, for example, if you're talking about Space Invaders, to the value that the state is going to have. And the value is basically nothing else but the return, right? In this situation, we are trying to basically approximate our value function that is quite complex with the neural network. And this neural network will, let's say, have parameters psi. Okay. So how do we learn such neural network? Well, we can learn it by fitting. Basically, we can define a loss function that tries to minimize how well our value function, how well our neural network is predicting the value of the state, given the returns that we have from our data set that is coming from the interaction of the agent with the environment, right? So I haven't explained exactly what this is, but it's basically just return of that you obtain from starting from state S and executing policy pi in that state. So you can technically read this out from the data. Okay. So this is just standard fitting problem, and it can be really helpful in order to reduce the dimensionality of the state space. And we are going to talk about this in the next part of this lecture. But for now, let me see if there are any questions. So there is a question: if you have continuous state, how can you input the states to neural network? So, for example, your state could be in the case of, let's say, car, your state can be a position, right? It can be defined by coordinates x and y. These coordinates x and y are continuous. They are defining continuous state, right? Because both x and y are real numbers. So how do you do it? Well, you just put as an input to a neural network these two continuous numbers. Okay. In the case of neural networks, what is the policy? The weights. Yes, so let me just go back here. Policy is always defined in mathematical language as a mapping from states to a distribution of actions. But a representation of policy is basically neural network. So effectively, everything about the policy is defined by the weights of a neural network. So you're right. Effectively, the policy are weights of the neural network, because once you have the weights of the neural network, you know how to map actions, states to distribution of actions. Of course, for this, you also need to know the architecture of neural network. Okay. Let me see if there are any other questions. Okay, good. Finally, we come to the third part of the lecture, which is about a system that achieves goals by learning. So basically, this part of the lecture is trying to implement what I discussed previously. And the first question that you might ask is, what actually are we trying to learn here? This is a really valid question, because there are different objects that you might want to learn. First of all, we might want to learn a model, right? Why would we want to learn a model? Well, we know how to find the policy if you know the model. We just saw this in the previous part of the lecture, right? We just plan over the model. So one way of doing reinforcement learning in this case would be to learn an approximate model and then execute planning procedure. And there are different ways of doing this, but in this part of the lecture, we're actually going to focus on model-free reinforcement learning techniques, which are trying to directly learn a policy or a value function, because we might need both, from the data. So we are not going through this intermediate step of learning the model. Okay, there's one more question here. The policy maps the state to the next state. The neural network does that. So yeah, I think there was a confusion. So let me clarify this. The policy doesn't map the state to the next state. The policy maps the state to a distribution of actions. Or in the case of discrete policies, you're mapping state to an action. After that, the model maps your action and the current state to the next state by sampling. So it doesn't do mapping, it samples from the distribution that defines how the world evolves over time. I hope this clarifies things, but feel free to post more questions if my answers were not clear. Okay, so what we are trying to do here is basically model-free reinforcement learning. Good. So how do we do this? Well, one way of approaching this problem would be to try to find an optimal policy. as I mentioned, we want to somehow try to figure out a way to directly find an optimal policy without constructing the model. So what is shown here in the first equation is basically the objective that we had before. I only replaced policy with theta parameters, and theta parameters here are parameters or are weights of the neural network. Why? Because we are searching over the parameters of neural network that is representing our policy. So this is the only thing that changed in our objective at the moment. And how do we now maximize this objective? Well, we can use standard techniques, right? What do we do in deep learning? Well, we just, let's say, performing a stochastic gradient ascent or descent. So we can try to do the same thing. Let me just do a quick reminder of how this would work in the case of policy optimization. So we would basically iterate over a number of iterations. And at each iteration, we would try to find the gradient of this objective function and push the parameters of the policy in the direction of the gradient. Basically, here eta is a learning rate. So this is basically just standard learning approach to, let's say, learning new parameters of machine learning model, right? I'm not doing anything sophisticated. So this is what you would do in standard supervised learning. However, the question here is, if you are trying to do this, what exactly is this gradient, right? We need to somehow be able to evaluate it. Okay, so let me try to give you an intuition what policy gradient methods are trying to do. So, okay, so going back to our objective, we can rewrite it in a way where we have a summation over possible trajectories, and then we modulate the return of these trajectories by the probability of them occurring in the world, right? So let me repeat this again. So our objective function, so this expectation, is by the definition equal to the probability that a certain trajectory gets rolled out in the world, that we have a certain sequence of state and actions over the time horizon h. So this is basically just a standard, I mean, this is by the definition, right? Times the return that we obtain from this trajectory. And we can calculate the return of trajectory because we know, because we are given this from the environment, right? All of these reward state 1, action 1 is also given to us by the environment when interacting with the environment. So this we know how to do. The question is, we know we can read this out from the environment. The question is, what do we do with this term, right? What do we do with the probability of trajectory given theta? We need to somehow figure out what it is. But interestingly, if you take the gradient of this objective function, right? So this is our objective function. We can take the gradient of it. If we take the gradient, we can, push it through the summation, right? So gradient of our objective function is sum of gradients of this probability distribution times r of tau. R of tau is basically return for the trajectory tau. Okay, so this is standard, standard calculus. And intuitively, what we have here is that the gradient is basically trying to increase the likelihood of trajectories, right? If these trajectories are giving us positive return, okay? So remember, we are going to eventually try to use this gradient to update parameters of theta, but what we are effectively doing here is we are increasing the likelihood of those trajectories for which this quantity, which is the return of the trajectory, is positive. Whereas if you have negative return, then we are decreasing the likelihood of those trajectories. Okay, let me just stop at this point and see if there are any questions. Okay, the neural network outputs the value to compute the loss, but I can't understand how it can output the value and the policy. I'm having trouble in distinguishing these. Okay, before proceeding, let me try to answer this. So you can define. I think I wasn't clearly explaining this part, but you can technically define two neural networks, one for policy and one for value function, right? In which case, you know, you wouldn't have this problem that you're mentioning here. So you would completely disentangle policy from a value function, and you would separately train policy and the value function. So basically, we have two neural networks. Value function would try to neural network would try to maximize the prediction of the return for particular policy, and neural network would try to, you know, optimize the return. So these would be completely different, separate objects. Now, often in practice, you can actually combine both of these, and we are going to see this in one of the following slides. So maybe keep an eye on so keep this in mind, and I'm going to show you this property later on. But you can do this. It's not something. So basically, policy and policy network and value network can share some parameters. This is not outrageous, I would say. Okay, yeah, but please do keep this question, ask this question again if things don't get clear later on. Okay, so this is basically let me continue. So this is basically an intuition behind the policy gradient. It always tries to somehow increase the likelihood of trajectories that are performing well. Now, what we actually need to do is we need to somehow, going back to this term, we need to somehow figure out what gradient of this probability of trajectory given theta with respect to theta is. We haven't defined this, right? I mean, this is completely unknown object at this moment. And it turns out that you can rewrite this gradient in a nice form in which you don't require model parameters. Now, I do have slides that are talking about gradient calculation, so I can show you later on after we finish with the main part of the lecture. But for now, you should trust me on this one. Or I can, of course, if you want, I can show you the full derivation later on. That we can rewrite this term. We can rewrite this term in a way that we obtain the following, in a way that we obtain something that is not dependent on model parameters. Okay, so basically what happened here is that this term was rewritten in terms of expectation in which trajectory is sampled from probability distribution of obtaining a trajectory given a policy. So this expectation is something that this trajectory is something that we obtain by executing the trajectory itself, right? It's our data point. So effectively, we don't need to care about this, right? This is given directly to us by executing the policy. What we do care is that inside of this expectation, there is nothing dependent on the model parameters, because we don't know model parameters, right? And that's important. And there is nothing dependent at this point on the model, which means that we are in the model-free regime, right? So what do we have inside the expectation? We have two terms. So one of them is return of trajectory, which we can directly read out from the environment. This is given to us by the interaction with the environment. And the second part is this gradient, a gradient which depends only on the policy. And we know how to do this in, let's say, deep learning, because this is typically what we do with, let's say, prediction task, right? For example, if you have a prediction task, you often try to minimize some kind of a cross entropy loss, right? And you're taking the gradient of this cross entropy loss, and this really resembles to this, right? Except that in this case, the prediction task is sort of the action that is going to be taken by the policy. Okay, so this is just some intuition behind it. However, importantly here is that we do weight all of these gradients by the return that we obtain by interacting with the environment, because we want to somehow steer the gradient also towards more desirable trajectories, as mentioned on the previous slide. Okay, but once we have this, we know what to do with this. We just now have to take a standard vanilla stochastic gradient approach to optimize policy. So how do we do this? Well, we initialize parameters theta. These theta will be basically effectively parameters of a neural network that is representing our policy. And then in each iteration, what do we do? Well, we first collect a trajectory or multiple of them, if you wish, by executing policy with the given parameters theta. And in addition to this, we also need to estimate the return of the policy. Okay, once we have that, we just need to estimate the gradient, and we know how to estimate the gradient. Basically, this is given to us by previous slide. So we just plug in this part in the gradient estimation, and we know that this is going to be an unbiased estimate because we are sampling trajectory from by executing the policy, right? So if you are sampling trajectory by executing the policy, and we are just estimating this part, we know that it's an unbiased estimate of the gradient. Okay, so basically this gradient estimate is an unbiased estimate, which means that we can just use standard stochastic gradient ascent to basically iteratively improve the policy parameters. Okay, so this is sort of a vanilla way of thinking about policy gradient. Now, this policy gradient is, let me actually first see if there are any questions at this point. Okay, there are no questions. Okay, now this policy gradient is, an interesting algorithm, but the problem is with the variance that we get in our gradient estimates. So if you just execute policy, let's say a few times, these returns that we are going to obtain by executing policies can vary a lot. I mean, we are searching over the full trajectory. And this is not good for reinforcement learning because, remember, in reinforcement learning, we are going to update our policy parameters, but then we are going to use that policy to provide us with the new data that we are going to use again for doing gradient descent. So this can be quite unstable. So now, without going into too many details, what you can do is, it turns out, you can replace, that is, you can do a series of calculations to replace this return with a different quantity, which is called advantage. And advantage is nothing else but difference between advantage of at certain state ST and for a certain action AT is nothing else but the difference between Q value for that state action pair minus the value of the state, right? This is the definition of the advantage. Now, in practice, what we try to do instead of directly calculating this from Q and V values is we are trying to estimate it from just one of these objects. For example, we can try to utilize a value function to estimate our advantage function. So if you remember what I mentioned a few seconds ago, advantage is a difference between Q values and V values for a given state action pair. V value part is here. Q value part, the estimate of Q value part is here, right? It's just that we are estimating it from, in this case, from one sample. Now, there's one thing that we haven't mentioned, and this is how do we obtain value function, right? Even if you define advantage with just a value function, the question is how do you obtain value function? Because this is what we need to calculate the advantage. Well, if you recall the previous part of the lecture, this value function can be, first of all, represented by a neural network. And then using the data that we obtained by executing a policy, we can fit a v-value. So we can try to learn v-values as well while we are learning the policy. So this brings us to a method called actor critic, or a class of methods called actor critic methods that try to use, in addition to optimizing policy with, let's say, stochastic gradient, they are trying to utilize value function to stabilize, that is to make the variance of the gradient smaller. So at the same time, they are learning both policy, which is an actor, and a critic, which is our value function. So how do we schematically do this? So we first execute policy, let's say pi theta in the world, and then we update pi theta with the gradient update rule, but utilizing value function that is also a neural network in our case. To do this, we need to also fit Q values, and we fit the Q values based on the data that is obtained by executing the trajectories. How do we fit it? Well, we fit it by minimizing, let's say, a mean squared error, which is what we had in the previous part of the talk. So for a policy that is describing value network, what we want to do is basically minimize its prediction, its error prediction, and prediction, the thing that value function is trying to predict is nothing else but the return from each state to, the final state. So basically, return here can be obtained simply by reading out our experience that we obtained by interacting with the environment. Okay, let me see if there are any questions at this point. Okay, good. So let's sort of just see how this works on a card poll example. So card poll is one of the simplest methods that you can find in OpenAI Gym. It consists of a cart that is of a pole that is connected to a cart. So pole is this object here in here basically colored in brown, and cart is a black object that is going on this line. And we are controlling cart, so we can either move it left or right. So our actions are either left or right. State of this system is described by 4 numbers: position of cart, velocity of cart, and then you have also angular position and angular velocity of pole. And the goal here is to keep cart vertically as long as possible. So this, keep pole as long as possible in a vertical position, and this pole shouldn't fall below a certain angle, right? So how do we define a reward for this system? Well, we can define it by saying that the system should keep this pole execute as long as possible in this environment, which would effectively mean that it keeps the pole above a certain angle. Okay, so that's nice. And this also goes back to one of the questions: how do we deal with continuous environments? Well, how do we deal with continuous states? Well, here the state is really continuous. It's about velocities, positions, and so on. Okay, now in order to execute actor critic, we also need to define both actor and critic. And actor here is a policy. So we need to define what the policy network is. And critic here is value function. So we need to define what value function is. In this particular case, actor and critic can have a shared shared neural network. So they have the same input. Basically, they have the same state. Then they have a shared first hidden layer, consisted of 128 neurons. And finally, they differ, their last layer differs in the output, right? So actor has its own output layer, which is based on softmax. Softmax meaning here that you're trying to use a softmax layer to define a probability distribution function over actions. In this case, we only have 2 actions, so the softmax has 2 outputs basically. And critic has its own output layer, which is just a single output, right? Providing us with a prediction of the return for each state. Good. So let me just briefly walk you through some of the relevant parts of the code of how one would code this in Keras. So the first part is basically based on the first part of this code is basically defining the neural network structure that is consisted of input layer, of course, and then you have a common dense layer of neural networks. In this case, we have 128 hidden units with ReLU activation. And they differ in the final layer, right? So you have a dense layer for actor with 2 actions, so with 2 outputs, and it uses softmax rule, basically because you want to obtain probability distribution function in the end. And critic has its own output layer, which just consists of 1 neuron. So basically, this is how we would define the neural network that is representing both actor and critic in this particular example. And then, apart from having all the code related to how you execute OpenAI Gym, the 2 most important parts here are to define a loss function for each of these. That is for the whole neural network, but you can also think of this as 2 neural networks with a shared hidden layer. So if you remember what the actor critic method does, it's basically trying to, it's basically taking a gradient of the policy, of log of policy, and it multiplies this with advantage function. And advantage function here is encoded in this diff variable. And we are taking negative here because previously we were optimizing the rewards, but in Keras what we are doing at the moment is minimizing the losses. So we need to take the negative sign of this. And critic is basically just trying to minimize here the prediction error, which is the difference between values that are outputted by the critic and returns that are actually obtained. Finally, the full loss function for this shared neural network system is the sum of 2 losses, and we just then take the gradients in the model and optimize using some optimizer. Good. So this is like a really brief sketch of how one would code this up in Keras. Okay, are there any questions at this moment? Let me see. Okay, regarding slide 41. Let me just go back. Sorry. 41. Regarding slide 41, what is the advantage of using a shared layer to train actor and critic instead of using 2 separate networks? Well, if you use a shared layer, then you have a smaller number of parameters to optimize. Of course, this is a really simple example, where we just have a I don't know, 128 units in the hidden layer. So we don't gain much from using the shared layer. But sometimes, if you're talking about more complex networks and more complex scenarios, we can gain in speed of learning, right? So the smaller number of parameters you have, the better it is, because you're of course obtaining a much faster learning procedure. So it's basically just in the number of parameters. Sometimes you can use, it depends on the practical application, but this is often useful to have in mind, because the smaller number, especially if you are using more complex neural network structures, then you definitely want to decrease the number of parameters in reinforcement learning, because these reinforcement learning algorithms can actually take you quite some time to train. So yeah, good. In the card-pult example, the image is the input for a network. No, it's not actually. This is actually not the case. So the input here is the state, and state is defined by 4 numbers. These 4 numbers define velocities and positions of cart and pole. So 2 numbers define velocity and position of cart, and 2 numbers define angular velocity and angular position of a pole. Good, great. Okay, so yeah, so far we investigated vanilla policy gradient, actor critic method, and let me just briefly mention an off-policy method. In this case, it's deep Q learning. I'm not going to go here into too many details, but I just want to mention that there is this different paradigm of utilizing some of the algorithmic approaches and make them less dependent on the policy on the policy executed when we are learning something about the system. So in the actor critic method that I mentioned, we were learning in a non-policy mode, meaning that what we were learning about the system was related to the policy that we were executing. So if you go back here, the value function that we were learning was the value function of the policy that we were actually executing, right? Now in off-policy learning, what we can do instead is, for example, this is what deep Q learning is trying to do. It's trying to learn about the optimal policy while potentially executing suboptimal policy, or potentially executing any policy that provides you with rich enough experience. As I mentioned, I don't want to go into too many details, but this is something that is quite interesting, because you can gain more data for the policy that you actually want to learn by, from experience that's from your past experiences, right? So if you're, for example, learning about the optimal policy, you can learn it also from the data that you obtained in the early on stages. So yeah, sometimes this is beneficial, so it's important to basically have in mind that there are also these types of algorithms. Okay, so having said that, there are also a bunch of other reinforcement learning algorithms. Here I sort of outlined reinforcement learning zoo that was taken from slides from UC Berkeley course on deep reinforcement learning, which I highly recommend if you're interested in this topic. And there is a good reason why there is a whole range of methods in deep RL. These methods basically can be classified, well, first of all, in 2 major parts. Either they're model-based or model-free. We discussed model-free approaches, but they differ in, first of all, in the number of samples that they require from the environment in order to learn sufficiently good policies. So the less examples you need, the more sample efficient you are. And typically, those methods that are based on model require much less experience. Like they require much less interaction with the environment in order to learn good policies. So we would say that they are maybe more sample efficient. However, we don't only care about sample efficiency. Sometimes we also care about wall clock time. These are two different concepts, right? Sample efficiency is good if you are sort of, for example, executing some of these algorithms in the real world, let's say on the robotic arms, right? So you want them to interact with the environment for, let's say, I don't know, 20 minutes or so. But sometimes you have a good models of the environment, and there is no reason why we wouldn't sort of do the learning completely offline on servers. And in that case, sometimes it's useful to utilize methods that maybe require more samples from the environment, but each interaction with the environment is more efficient, like evolutionary methods. They don't even use gradient. They don't even calculate gradient when they're interacting with the environment. And at the same time, we can parallelize them really efficiently. So that's something to have in mind. If you can sort of parallelize your system, then maybe sample efficiency is not what you care about. Whereas if you want to deploy some system in practice, maybe model-based approaches can help you a lot. So, for example, if you have a really good model, if you have a really good physics model of a system, there is no reason why you wouldn't use actually that model as your prior knowledge, and then just tweak some parameters. All right, so this will give you a lot in the speed of learning. Okay, so maybe for the final part of the lecture, for the last 20 minutes or so, I can just provide you with some fun examples of reinforcement learning. So the first one is the example that comes from Cole and Stone from 2004, where they try to utilize policy gradients in order to learn the gait of this quadrupedal robot. So as you can see, in initial periods, this robot is actually not performing very well. I think the robot itself has 12 parameters that are important to make to optimize over in order to make this walk done in a smooth way. So what they did is basically they deployed policy optimization technique. This policy optimization is slightly different than what we discussed. After some training, what you obtain is the following behavior. So it's somewhat different than what we discussed in this lecture, because it actually also estimates the gradient itself. It doesn't use pre-calculated gradients. But there are other examples that do the same, only on different environments. So this is environment Mujoko, which is sort of like a environment for continuous control, where you can control these different sort of robots. So these robots are basically, what you're controlling in these environments are the torques of the joints, right? And interestingly, the reward here in this particular environment is basically defined by how fast the object moves. So you can see it actually performs quite well for some of the objects. Maybe I can put humanoids instead. So you see you obtain some kind of interesting behaviors. By the way, for the previous example, the reward was also the speed of progress, right? How fast the robot was walking. This was sufficient in order to make that robot walk in a way that was at that point state of the art. Okay, and maybe as a final example, I would like to show how deep Q learning operates on Atari games. So Probably you've seen this example. This is a game called Breakout, where you control a pedal. You either move it left or right. And the goal is to, basically hit with the ball all these objects above the agent. As the image, they use state space as defined as the image. So a policy network, that is, in this case, it was not policy network, it was just a queue. Queue function was defined through convolutional neural networks. So once you train the system for some time, you can obtain actually quite impressive results, as you can see in the video. Okay, okay, so what we did in this lecture was basically, first of all, formalize the model based on Markov decision process. And then we described 3 methods related to reinforcement learning. One is imitation learning-based method called behavior cloning. This method is it's often practical, right? But it requires a large demonstration data set for some environments. Then we discussed planning methods, such as policy iteration. And finally, we talked about model-free reinforcement learning methods, such as policy gradient and actor critic. And let me check if there are any questions at this point. Okay. Okay, there are no questions at this point, so I'm just going to briefly introduce some of the interesting points that might be relevant for the next lecture. By the way, they're like, I used a lot of references to create this presentation. As you can see, they contain both papers and book chapters. I would highly recommend for learning about reinforcement learning, the book of Sutton and Barto, An Introduction to Reinforcement Learning. And as I mentioned beforehand, there's a lot of interesting material on deep reinforcement learning that comes from UC Berkeley. So you have this UC Berkeley course on deep reinforcement learning. Okay, so what we haven't talked about in this lecture are basically the systems that can achieve goals in a wider range of environments. So we would, in this case, have an agent that would interact with multiple environments, not just one, right? So what we discussed so far was a single environment described by an MDP process. So the question is, how do we do interesting tasks along this direction? And one possible task would be to quickly adapt at the execution to the specifics of each of this environment. As I mentioned before, these environments cannot be completely different, right? If you want to make anything useful out of reinforcement learning. So a wider here has to be somehow defined. But if these environments are sufficiently correlated, then what we could possibly do is learn a policy, at least learn sort of a meta policy that we can utilize to quickly adapt to each environment using a small number of interactions. So the way this process would go would be that, the idea would be as follows. So we would have an agent that utilizes some policy pi theta that is parameterized by theta parameters of, let's say, neural network. And then we would interact for a bit with this environment K, after which we would maybe perform a few gradient steps to update policy pi theta to policy pi phi. After which we would require that this new policy behaves, it produces good behaviors in the same environment, right? So this would be our goal. Our goal would be to somehow optimize this return after the adaptation step. So of course the question is, how do you do this? And I would refer you for the details to, for example, one of the publications on meta reinforcement learning. This is just one view on meta reinforcement learning called model agnostic meta RL. Model agnostic meta learning. So this is by Finn et al. In 2017. But I do want to sort of point out that these types of approaches do go into the direction of making an agent operate well in the diverse set of environments. In the next lecture, however, we are going to take a different perspective on this, and we're going to try to go towards a system that achieves goals by learning in a wider range of environments. And here, the environments are put in gray because they are more like effective environments from a single agent perspective. So this will actually bring us to a multi-agent reinforcement learning framework, and we're going to try to showcase the difference between single agent RL that we described in this lecture compared to multi-agent reinforcement learning that has this additional complexity where we are sort of also dealing with the presence of other agents. As we're going to see, these other agents are sort of from a single agent point of view are basically are basically an effective environments of that single agent. Okay, so let me see if there are any questions. I think we have still 10 minutes to go for the Q&A session. So yeah, any comments on OpenAI in Dota or other competitive games, 1 versus 1 and 5 versus 5? Yeah, this is in part going to be mentioned in the next lecture. These are definitely, I would say that this belongs to this belongs to a framework of multi-agent RL rather than single-agent RL. I would say, I mean, these are really impressive results, especially in recent years. We also had improvements along the direction of making agents basically work for StarCraft, which was considered to be a few years ago really challenging environment. I'm not going to talk about specifics of these results. I'll maybe mostly focus on one of the earlier works along the direction of competitive games such as Go. But yeah, it's important to have in mind that these are all significant progress that are being made in the last few years. Okay, maybe I can also try to answer the last question that remained here. How well does transfer learning work for multi-agent approaches? Could we use one baseline, a trained model, and then fine-tune several agents that work together? Yeah, that's an interesting question. Let me first try to answer the second one. Could we use one baseline and then fine-tune the agents that work together? Sort of this goes along the direction of meta reinforcement learning, right? You have sort of a single agent that you can, with a small number of interactions with the environment, that you want to fine tune to operate well on the different environment. So in the context of transfer learning, I would say I would maybe first mention that one of the most interesting parts in the context of transfer learning was in my opinion is this initialization of good prior policies. So you can sort of start with the goods policy from imitation learning and then obtain sort of fine-tune the final policy by reinforcement learning, as we'll see in the next lecture. In the context of transfer learning for multi-agent RL, yeah, I would have to think a little bit more about the exact results. I don't have something particular in mind, but I should mention that the way these latest results are, I would say the robustness of these latest results really relies on the fact that you are somehow using populations of agents to train other agents, so that you are sort of robust against your opponent. Yeah, so I guess this partly answers your question. Any other questions? Yeah, but I would have to think a little bit more about the first part of your question.
Okay, so now we have a break for 30 minutes, yes?
Okay.
And then we'll come back. Thanks.
Thank you. Should I share my screen?
Yes, we have 1 or 2 minutes. Okay, I think we can start.
Okay, great. So, just a second. Okay, I think everything is okay. Okay, so welcome back to the lecture on multi-agent reinforcement learning, to the second part of it. Now we are going to try to combine reinforcement learning with multi-agent systems. So just a few words on multi-agent systems. If we take a look at the definition on Wikipedia, multi-agent systems are basically computational systems that are composed of multiple interacting intelligent agents. These agents are often also self-interested, so they have some reward function that they want to maximize. And there are many examples of multi-agent systems in practice, ranging from ad auctions to crowdsourcing, or even kidney exchange as a form of multi-agent system that is present in the domain of health. So the reason why we care about studying these multi-agent systems first of all because they are present in the world, right? You have often autonomous agents that are making decisions on their own, and secondly, sometimes it's also useful to have multi-agent systems as a design. These systems are, in a sense, robust because you can easily replace components that are broken if you have this modular design. On the other hand, you also have, there are also challenges with multi-agent systems, including incentives, for example. So there is often a reward misalignment between agents. So the question is, how do we incentivize agents? If you are designing a system, how do we incentivize agents to cooperate? So the goal now is, to somehow combine this system with the reinforcement learning framework. And this brings us to multi-agent reinforcement learning. So let's go back to what we had in the last lecture. In the last lecture, we had a single agent that was interacting with the world. It was perceiving environment, and it was acting on the environment, and its action on the environment would basically change the environment itself. And this procedure was, repeated. So the agent would repeatedly act in the environment and make some decisions based on which environment would change its states. The goal was to sort of map what an agent observes to actions in a way that the agents, first of all, achieves the goals and achieves them in an optimal way. In the multi-agent system, we have multiple agents that try to do the same thing, right? They are sort of trying to interact with the environment over a period of time, make their decisions in a way that they possibly optimize their payment. So first of all, there is this setting is at this point somewhat ambiguous because it's not clear what our objective is at this point, right? So it really depends on the specifics of the setting. So these agents can, for example, be controlled by one entity. For example, if you are designing our own multi-agent system, we might be in control of all of them. In which case, we might want to optimize the joint reward. We might also be in control of only one of the agents. In which case, we have to design it in a way that it accounts for the presence of other agents in the world. And finally, we might be in the control of only one agent, but other agents might also cooperate with us. So there are all of these different scenarios that are sort of specific instances of multi-agent settings. If you take a perspective from a single agent, effective environment that a single agent has in its view incorporates other agents. And this is what makes actually the problem challenging, because now this agent needs to account for the fact that other agents might be responding to its behavior, right? The environment now is not just static in a sense that, sure, it evolves over time based on agent action, but it's not just static in that way. It also accounts for, what other agent is trying to do, right? So sort of environment itself is responding to the changes of the agent's one policy in a way. Okay, so we have inherent non-stationarity in the system, right? This means that sort of effectively what we are considering here is environment or task that is potentially evolving over time. So if you are in particular in a multi-agent reinforcement learning setting, agent one surely is learning, but also other agents are learning in the world, which means that an effective environment of agent one is evolving over time, right? It's evolving because other agents are changing their behavior, or it might be even evolving because other agents are different types of agents, right? So these agents, you're interacting with not just agents A2 and A3, but you're also interacting with some other agents A2 and A3, so on and so forth. And we have somewhat similar situation when we were talking about multitask setting, right? When we were talking about meta learning, in particular meta reinforcement learning, we are considering the case where these tasks, where we had like multiple environments or multiple tasks, and we're trying to design an agent that can sort of quickly adapt to each of the tasks. So obviously this framework might be interesting for us, but I do want to point out some of the differences between multi-agent RL and multi-task setting. However, notice that we have here, effectively multiple tasks at hand that we want to solve, right? Simply due to the presence of other agents. So, when I mentioned that in this part 4, we're going to talk about system that achieves goals by learning in a wide range of environments, this is what I meant. Like, effectively, other agents are creating environments for the single agent that we care about. But we should be careful here to not confuse, multi-environment, standard multi-environment setting with multi-agent setting. So these are sort of not the same settings. In a sense, you can consider multi-agent setting to be a special instance of multitask environment, but it does make sense to analyze multi-agent setting as a specific case, and I'm going to try to show this in the following slide. So basically, what I was talking about is that up until this point is that a multi-agent multi-agent setting is sort of, first of all, different than single agent setting because you have this multiplicity of tasks that you want to solve. There is multiplicity of environments that one wants to interact with because of the presence of other agents. But it is important to also take into account this fact that these agents are not creating just arbitrary tasks. They are sort of utilizing. They also have, let's say, their own reward functions, their own learning procedures. So the question is whether we can exploit the structure of these effective environments from the perspective of a single agent case in order to design algorithms that are better. And I'm going to try to showcase this, that indeed it does make sense to study multi-agent setting as a separate setting. And we are going to see this also later on, that in the cases where it might be difficult to actually find a good policy for a given agent. When the environment is changing in the multi-agent setting, if these effective environments are changing in a way that we might be able to cope with the non-stationarity. But it is important to account for non-stationarity of environments that come from the fact that there are multiple agents in the world. Okay. Good. So let's first consider the case of repeated interaction. So in this repeated interaction, we have I'm going to explain a really simple setup where we have a single agent that interacts with the environment that evolves over time. So at each time step, this agent decides on its policy, and that it is going to use to interact with the environment that has only single state, right? So this is a much simpler environment than what we discussed in the previous lecture. It has a single state. So how can then an environment evolve over time? Well, it can evolve over time by changing its reward function. And we are going to assume a really interesting case where these reward functions are not known a priori to the agent, which is a similar situation that we had for meta-learning, right? When we were considering meta-learning, the agent was first interacting with the environment for a bit and then was trying to adapt to it. But it was actually first so this agent was first trying to sort of explore a bit in the environment so that you can adapt to it, right? It didn't know everything a priori, right? And the same thing we have here, right? We don't know the reward function itself. So it's also quite general scenario because reward functions here can be relatively arbitrary. So what can we do in this case? Well, we obviously cannot, optimize. If you don't know anything about reward, then it's kind of hard to say that we can be optimal with respect to each possible environment separately. But what we can do instead would be to somehow minimize the regret that we have with respect to some fixed policy. We can now introduce the notion of regret, which would say the following. We are going to fixate some policy pi star, and we are going to compare ourselves in terms of the total reward with respect to this policy pi star. Right, so we're going to first calculate the policy of pi star, but also calculate the policy that an agent that potentially changes its behavior over time as it interacts with the environment obtains over some time horizon t, right? And of course, we're going to here try to calculate the worst case scenario. So this should be exchanged. We should actually put RT pi star minus RT pi t. This is a typo. So we are going to try to find the worst case requirement for this regret, meaning that we are going to try to find a policy pi star which sort of maximizes this notion of reward differences. Okay, so how do we do this? Well, we can utilize online learning algorithms, and one of the online learning algorithms here is optimistic follow the regularized leader, which is discussed, for example, in Silkanis et al. in their 2015 paper. So how do we come up with the policy? Well, what we are going to try to do in this optimistic follow the regularized reader is basically an optimization problem where we are trying to find a weight vector. Weight vector here is a weight across different states. This weight vector will try to maximize the dot product between itself. And so we are going to try to maximize the dot product between this vector across different actions and this sum. And this sum is basically a sum of vector of rewards. It doesn't really matter that much if you don't follow the details here. But the main point is that we are somehow using the history of interactions between the world, and we are also biasing this history to include the last reward function twice. Here R is standing literally for the reward function, which can be described by a vector of reward. Sorry, this is a vector of actions. So it basically describes the probability across the distribution of actions. And this vector here is a vector of rewards across different actions for each time step. Okay, and if you deploy this algorithm, what you can show is that the regret of this algorithm is O of square root of t. Okay, let me just see if there are any questions at this point. Good. Okay, so now we can ask a question of, how does this algorithm perform when we have multiple agents? So to do this, let's consider the repeated game setup. Okay, so first we are going to consider a single shot scenario where agents just interact within a single time step, right? And we can try to utilize the classical game. This game is basically displayed here in normal form, in a normal form, right? So basically as a matrix. Let me just briefly walk you through the normal form of this game. So basically we have two agents. They have actions. Agent 1 has actions A, B. Agent 2 has actions C and D. And the reward of this matrix, the first component is the reward of agent 1. The second component is the reward of agent 2. So if these agents are somehow planning in their mind what they should do, it ends up being the case that they should play the following strategy profile in which agent 1 plays action B and agent 2 plays action D, right? And you can actually verify that this is an equilibrium of a game. So let's try to do that. So for the first agent, the best response action to the action of agent D is action B. Why? Because if agent 2 plays D, then agent 1 maximizes the payoff by playing B. On the other hand, if agent 1 plays B, the second agent also maximizes the payoff by playing action D because 1 is greater than 0. Okay, but what if these agents are learning, right? How would we describe this situation? I mean, we do care about the learning processes in multi-agent reinforcement learning. So the way to do this would be to introduce repeated games. So repeated games are basically repeated interactions between agents where in each time step they play the same game. So here, what we have is an agent 1 that is interacting with agent 2, but effectively it's interacting with its effective environment that changes over time, right? This is something that we've seen before, right, in the repeated interaction case. The goal, of course, now is to see whether we can learn efficiently to interact with this changing environment, right? So you might think, okay, it's the same setup. I mean, what can we do? We can just apply, let's say, OFTRL algorithm. It will give us basically the same guarantees. But actually, it turns out to be the case that if both agents use this algorithm, OFTRL, The regret of agent 1 is of order OT to the power of 1/4, right? For a specific structure of these games called smooth games, but the notion of smooth games, smoothness in game theory, it's well established. So this is not, for example, if games are just zero sum, you can sort of do the same. This result will hold, for example, for zero sum games as a specific case that aligns with the structure. But the point is that, at least there are games for which this result holds. So basically, multi-agent setting seems to be somewhat more specific case of a changing environment, right? So it makes sense to analyze it because we do obtain some games, at least in this particular setup discussed by Silkanis et al. So this result is shown in this reference. Okay. Of course, what we want to do in more general scenario is, we want to somehow showcase that the same thing basically holds when we consider a more general setting, which is not just repeated games, but based on games and Markov decision processes. Right. So let's try to introduce this. So let's go back to Markov decision processes where we had a single agent that is interacting with the environment. So this is just a reminder from the previous lecture. We had agent that was following certain policy pi, and this policy pi was basically telling an agent how to react to the state of the environment ST. So an agent would sample an action AT based on this policy, and this action would then basically lead to a certain reward dependent on the reward function. In the third case that we discussed in the last part of the lecture, we assume that an agent doesn't necessarily know this reward function, right? Our agent didn't have this information; it actually had to learn it. Also, I like the specific case of the environment analyzed in the repeated game, which we just had one state. In the Markov decision process, we have possibly multiple states, and we sort of transition from one state to another according to some transition dynamics that depends on the current state and played action AT. Right. So this is just a recap from the previous part of the lecture. Our goal was to find a good policy pi. And more specifically, our goal was to optimize long-term discounted, long-term reward, meaning the sum of discounted rewards over some time horizon. Okay, so how do we generalize this? Well, once we put another action or more actions in the setting, some things change, right? So the second agent has basically the same sort of protocol of interacting with the environment. It receives states, it takes actions according to its own policy, and then it receives reward. But now, unlike in the previous case, actions here, actions of both agents now affect the environment, right? In particular, they affect both rewards, and transitions. So state changes based on the actions from both agents. And furthermore, also rewards of each of the agents, which are in general different, is dependent on the actions of all the agents. So, we have basically in this particular case, three objects that are changing: transition dynamics with respect to Markov, decision process. Basically, three objects are changing. So we have here transition dynamics, which now depends on all of the actions. Reward of the first agent, which now depends on all of the actions, and also the reward of the second agent, which again depends on all of the actions. Okay, so now the question is, okay, what should be our goal, right? Well, it really depends on the scenario, as I mentioned before, just like in multi-agent settings. You know, there are different objectives that we might want to reach. One objective is to maximize the payoff of a single agent, for example, agent one. In this case, we would want to find a good policy for agent one, given that, you know, somehow agent two is responding to our policies. I mean, there are different notions of what this response model would actually be, but you know, this is sort of like a generic setup, right? We want to optimize with respect to policy one. We are only controlling agent one, but we are somehow also thinking about agent two. Another objective could be that, you know, technically we are in control of all these agents. We want to find a good joint policy, but there are too many agents in the world. We are going to talk in a little bit more details later on about the setting, but basically, you know, they share the same objective. They have maybe either one utility function, or maybe want to optimize their social welfare, meaning that you want to optimize the sum of shared rewards. Okay, so it's important to notice here that basically we have different possible objectives. So let me just check if there are any questions in case things are unclear at this moment. Oh. Okay, so what are the practical examples that one can see incorporating some of these modeling assumptions into their frameworks? So probably canonical ones are games, as we also mentioned in the previous lecture. Some of you asked. I mean, this is a place where reinforcement learning had quite a lot of success, right? But games are inherently multi-agent. You have an agent and its opponent. We'll talk a little bit about this setting, although the focus of this lecture won't be entirely on it. And you have games like Go or chess or StarCraft, you know, and anything of that form. Second of all, we can have also practical scenarios where we want to do some cooperation, right? So, for example, in this really nice survey by Zhang et al., they mention as one possible practical application control of unmanned aerial vehicles, such as drones. You know, you can think of this as maybe a single agent problem, but as you'll see, it's maybe not practical to utilize a single agent point of view when designing these systems. So even though you could technically do it, there are practical reasons for actually trying to utilize multi-agent view to resolve this problem. There are also scenarios in which you utilize simulations to derive some interesting results. For example, Zhang et al. Talk about the AI economist. So here, in general, like you could have a multi-agent setting where, for example, you're trying to analyze some mechanisms or norms or policies of a principal agent that would be imposed on an agent that are also reinforcement learners. So both principal agent and these other agents are reinforcement learners, and what you want to do is maybe analyze the quality of norms or general mechanisms that this principal reinforcement learner might impose as basically on the other agents. This is something that I think was also analyzed in Zhang et al. From the context of social planner, right? Social planner was one planner reinforcement learning agent, and then you have also a bunch of other reinforcement learning agents that are modeling maybe humans, how humans would respond to different designs of social planner. And then something that I also worked a bit on, we could also think of human AI collaboration as a multi-agent setting, as also mentioned in the previous part of the lecture. So you have here two agent system. One of the agents is an AI agent that you are designing, and the other agent is a human, which we do not fully control, but we need to account for it. And you'll see actually that this might be quite important. So let me briefly walk you through some categorizations of multi-agent systems. The one of them is based on the setting, where we could consider settings which are competitive, cooperative, or mixed. Competitive settings are settings, for example, those present in games such as Go, where one agent has an opposite goal of the other agent. So every gain that agent one receives is basically lost for the second agent. Then you have a fully cooperative scenarios where agents share their goals, share their rewards. And finally, we have a mixed setting where agents need to decide when to cooperate and with whom to cooperate and with whom to compete. In this lecture, we are going to mostly focus on either competitive or fully competitive or fully cooperative setting. Okay, but there are also different possible axes that you can use to categorize multi-agent reinforcement learning scenarios. This one comes from Hernandez, Leal et al. It's also a really nice white paper on multi-agent RL, highly recommended to read. There they sort of suggest that some of the most recent papers on multi-agent RL analyze sort of one of the four aspects of multi-agent reinforcement learning. So, for example, they analyze emergent behaviors, where you have a single agent reinforcement learning algorithms. So here, really, the goal is not to construct a single reinforcement learning algorithm, but it's more like a descriptive approach to multi-agent RL. You want to sort of figure out what would happen in a different domains if you had multiple agents that are just standard reinforcement learning agents. Then you have also communication, like how does a communication emerge? What would be, for example, this might be interesting for cooperative scenarios, because sometimes if you have like agents located in distant locations, you want them to communicate to learn more effective policies. There's also cooperation among agents. So in this case, agents are fully cooperative, as I mentioned beforehand. We want to design, let's say, factorized policy, meaning that you want to have a possibility of decentralized execution of policies in agents, while sort of having control to some extent of the learning processes that these agents have. And finally, also there is agents modeling, in which we want to, from a single agent point of view, design good models of the second agent so that we know how to respond to them. This is, for example, important, as we'll see in human AI collaboration, where we are sort of trying to figure out what the good collaborative policies are for AI agents. Okay, in this lecture, we are going to mostly focus on cooperation and agents modeling from these topics. Okay, so let me see if there are any questions at this point. Okay, yeah, so let's start. So this lecture will cover basically three topics: multi-agent RL in competitive games. I'm just going to briefly sort of explain some principles, but not dive into too many details. Cooperative multi-agent RL. I think this is also quite fascinating topic. And finally, also, I'm gonna briefly, not briefly, but I mean, this is going to be a third part of the talk, agents modeling multi-agent RL. Depending on how we progress over time, I might skip some parts of this lecture, but I'm going to try to cover as much as possible. So let's start with the first one. So To do this, to describe multi-agent multi-agent competitive settings, let's consider this sort of arguably one of the simplest possible settings, in which we have reinforcement learners that are trying to interact with each other through the environment, which is a game. So in this case, we have zero-sum scenario in which a gain of one player is basically loss for another player. So that's an interesting. But if you are considering games, often these games have specific structures, such as chess, right? They are deterministic games, so there is no reason why not to utilize the specific structure of these games. So let's try to do that. So how could we model chess? So for example, chess could be modeled in the following way. So we could consider it as a two-player game. So we have two players. States would be positions and turns, positions of figures and turns of players. So we need to sort of also specify whose turn it is when we are analyzing the state of the game. States can also be, to some extent, special. So we have a special terminal states that define when the game ends. And for chess, this would be basically defined by this if operator. So if you are if there is a checkmate or there is a clear draw, then this would define a terminal state. Actions would be defined through legal moves of chess. Transitions are, as I mentioned, deterministic and defined by chess rules. It's actually we can actually define them implicitly. We don't need to sort of define maybe this transition matrix that we typically do for Markov decision processes. And then we also have rewards. As I mentioned on the previous slides, these rewards are defining a zero-sum game, right? So reward of agent 1 is basically negated to reward of agent 2. Importantly, rewards are basically zero all the way until the terminal nodes. So we can sort of define a state-based rewards function, right, which are not dependent even on actions, but for terminal nodes that they are either -1, 0, or 1, depending on whether we are talking about wins or losses or draws. So -1 denotes losses, 1 denotes wins, and 0 is a draw. Okay, so okay, at this point, I mean, you might be wondering whether, I mean, we do know chess rules, right? We do know rewards. So the question really here is, why do we need reinforcement learning? I mean, why don't we just utilize something like planning or search, right? So let me try to showcase this on using the following example, which well, you can consider like an example where we utterly simplify chess by having a turn-based game with these two players, A1 and A2. The first turn, in the first turn, A1 selects action, and the second player selects action. There is a second agent select action. And the third one, the agent A1 again selects the action. And after that, the game terminates, and these agents only have two possible actions, right? They can go either left or right. So after they execute their actions, we receive basically payoff. So all of this is encoded in this search tree. And the final node, these terminal nodes basically encode the payoff, that is the reward of agent A1, right? So the question now is, how do we decide, let's say, on a strategy for player A1? Well, we can just do backward induction. So starting from the last choice node of A1, which is in layer 3 of this search tree. We decide always to take actions where A1 would win, right? So we can do that basically for all of these nodes except this one. So in this node, A1 is bound to lose, and we can choose whatever action. It doesn't really matter. But for all the other nodes, we can definitely select an action that leads to player one winning the game. Okay, so what do we do then? So then the choice is on, so once we know what agent A1 would choose, because it's a rational agent, it would choose to win, we estimate what agent 2 would do, right? And for agent 2, effectively terminal node now is the one below. The terminal nodes are basically the choice nodes of agent A1 in the third level, right? Because we know what agent A1 would do. And here you can see the payoffs that agent A2 would gain for its actions. And in this case, for these two choice nodes, agent A2 can win here. Agent A2 will lose here, but it can win here. So it selects an appropriate action here. It doesn't matter what it selects here, but let's say it just selects the right action. And we just proceed with this reasoning further on until we reach a root node. And in the root node, we know what agent A1 would choose. It would choose to win. That is, it would choose the action go left, right? Okay, so basically with this reasoning, which is called minimax search. So this is sort of just an illustrative way of explaining minimax. We can find out what agent A1 should do in the root node and so on. What for each of the choice nodes, you can technically find out what each agent would do. Okay, so that's good. This minimax is actually optimal in the sense that if you assume that the other agent is optimal, we can construct an optimal first agent, our optimal agent. And that's great, but the problem is that it's simply too complex to perform it, right? So the time complexity is just too big. You basically end up searching through the whole tree. And it's infeasible for many of these interesting games, including, for example, chess that we discussed this, before. So really the question is, how do you levy this problem? So, okay. So again, I'm not going to go here into too many details, but these are just some of the principles that one can utilize in order to make a better search. So of course, we can first of all rely on better search methods. I mean, you know, we can utilize pruning, such as alpha beta pruning. So in pruning, I mean, the basic idea behind pruning is that, you know, you don't need to explore all possibilities for each of the action or for each of the agents. So if in a certain choice node, an agent already finds out its optimal action without exploring all possibilities, we know that we don't need to explore other possibilities at that point. We can just prune the subtrees that are not relevant. More sophisticated methods nowadays utilize sampling, such as Monte Carlo tree search. And the basic idea, you know, is, we are going to somehow figure out which nodes are valuable by randomly rolling out our policy until the end of the game. Okay, so so that's great, but some of these, but really the interesting part. So I could, of course, go and explain this in more details, but let's not maybe dive into too many details. Let me just emphasize that for the search method, for example, that are utilized in Go game, there are two other principles that are actually enabling us to limit the search space, and this is basically the whole point of trying to find out the better search method. Right? We want to somehow limit the search space by either limiting the depth or limiting the breadth. So how wide we search in the tree. Right, so we either want to somehow figure out early on whether some nodes are good by learning their value function. So value function is, if you remember from the previous lecture, value function is something that is sort of identifying the return of an agent if you roll out the policy of an agent after that state. So we can, the goal here would be to use some object like that in order to figure out whether we need to even go to that node, right? Whether that node is good. This is sort of a way of limiting the depth, and limiting the breadth is basically achieved by somehow, for example, in the sampling method, by somehow guiding the sampling procedure, right? Not exploring everything uniformly at random, but maybe sampling by putting more weight on more promising nodes. And effectively, this is in games like Go achieved through for value functions. It's achieved through learning the value function, learning a good value function for choice node, that is for states, and guiding this search, so making sampling procedure more informative, is effectively achieved through using good prior policies. For example, in the first Go paper, in the first this AlphaGo paper, what they effectively do is they're trying to construct a policy from good prior policy from human data, right? So this is what I want to maybe discuss on the next slide in a little bit more detail. But are there any questions at this point? Let me see. Okay, no questions. So yeah. So how does this work? So how do we obtain these policies? So prior policies are first of all obtained by imitation learning. We mentioned how the imitation learning works. So you basically use an expert data and you try to perform imitation learning, such as behavioral cloning. So once you have this, you have a good policy for sampling. So this is a policy that can sort of guide your sampling procedure towards better terminal nodes. So basically, it can provide you more informative sampling procedure, right? And by this, you're sort of limiting the breadth of your search. The second part is, also construct good value functions, which can sort of limit also the depth of the search. And the way to do this, at least the way the first AlphaGo paper did, was by first improving the prior policy, right? By using reinforcement learning, and then evaluating this reinforcement learning policy, right? So for the second part, where we want to find a good value network, we want to do this by reinforcement learning procedure. Now, here's the question. You have basically, this is not a single agent system anymore. So the question is, how do we perform reinforcement learning? And moreover, we don't actually have the optimal second player. We don't even know about it. So to deal with this issue, what one can do is basically self-play. So in self-play, we are replacing the agent 2, which we don't know how to model, because we don't actually have it, right? We don't even have a data for it. We're replacing it with the copy of agent 1. Now, this copy of agent 1 can either be like the current agent 1, or maybe some prior versions, or some combination of it. But the basic idea is that, the agent A1 is competing against itself, right? And effectively, what this is giving us is a curriculum, right? Curriculum for agent 1, because agent 1 now interacts always, or learns always with by playing against an opponent which has a similar skill level. So that's good, right? Because this curriculum is not only like, it's not handcrafted, it's sort of automatic way of figuring out how to provide opponents for agent A1 in a really, really simple manner. However, this way of sort of reasoning about self-play in terms of curriculum also poses some question whether this principle can be generally exploited. And it can be exploited when you have some kind of a transitivity, right? When transitivity in a sense of quality of an agent. So if agent A1 is better than agent A2 and agent A2 is better than agent A3, then the transitivity would tell us that agent A1 is better than agent A3. But this doesn't always hold, right? It really depends on the game structure. Okay, good. So let me just give maybe a little bit more technical point of view on why gradients work. So, for example, again, why do we care about having opponents of a similar quality, that is of a similar skill level? Well, if we have opponent that is too weak, then the returns that an agent would obtain are with basically high probability equal to 1, right? And then this whole gradient is more or less 0, right? Because you have a constant. If you have some opponent that is too strong, you have basically the same effect, but it comes from the fact that opponent is too strong will cause an agent to lose more or less all of the time, which means that this return will with high probability be equal to 0, which in turn means that the gradient is equal to 0. Okay, and self-play somehow provides informative gradients for better, more formal characterization. I refer you to Balduzzi et al. Reference. Good, so maybe I can check if there are any questions at this point. Okay. Yeah, so what I wanted to say here is that, I mean, in these games, which you can actually, in principle, solve by search methods, deep reinforcement learning is important for scaling them up. And I think the interesting part here is that, I mean, I at least find it interesting, this curriculum design of self-play. But self-play, you know, is not always, it's not always a method that one can use to train, to perform effective training. As we'll see later on, it doesn't always work very well. And this has also been noticed for more complex games. So if you take a look at Alpha Star or team-based games such as Capture the Flag that is shown on the right-hand side, you typically want to make improvements over such a design. Yeah, so I also wanted to mention there are other types of games, team-based games such as Capture the Flag, where you have teams competing against teams, and you're sort of trying to, let's put it this way, design reinforcement learners that can play well within a team against an opponent team. And the team that is, I mean, against other opponent team, right? So also games can be cooperative. This is Hanabi. There was actually recently an Hanabi challenge announced. I put some references related to these types of games in one of the last slides. And this basically brings me to the second part of the lecture, where we are discussing cooperation among agents. I should also mention that I think in the last lecture somebody asked questions regarding these more complex games. I didn't put material related to them, but you know, they are basically sort of they can be categorized within this first part of the lecture. Okay, so in the second part of the lecture, we're going to talk about a little bit different design on multi-agent reinforcement learning system. in which we have a cooperative setting, meaning that agents are now fully cooperative, so they share the same reward. But there are challenges in this design that come from scalability issues, as well as decentralization issues, right? So first of all, now often in these scenarios, we no longer assume that state is fully observed by an agent. So it's often partially observed, meaning that an agent just sees the parts of it and it doesn't see the same parts as the other agents. So the challenges here are to basically cope first of all with large action spaces. So if you have many agents, your actions are growing exponentially with the number of agents that you need to control. So, you know, it's not easy to actually optimize, find a joint policy that these agents would have given the complexity in the action space. But at the same time, you know, if you want to have a multi-agent setting, you have to take care of the fact that often you just receive some notion of global reward. So agents have the shared common reward, but this reward is not split among them. And finally, you know, we care about decentralized execution, meaning that these agents should act separately in the world. And if they observe different parts of the states, you know, they either need to somehow communicate all the information between themselves, or their policies should account for the fact that they are not seeing everything, right? And at the same time, they need to cooperate. So this is sort of an issue with partial observability, right? Okay, so what's maybe the simplest way to go about designing cooperative agents? Well, one of the simplest way would be to maybe just simply train these agents independently from each other. So basically just utilize the reinforcement learning independently on each of the agents. So this is great. I mean, in a sense that it's a simple procedure, it's computationally efficient. You know, you can effectively, there is like, you're just basically utilizing what the existing tools from reinforcement learning. The problem is that there's no explicit coordination among agents, right? So it's not clear why would this actually work. In fact, Tan in 1993 was analyzing the difference between independent training and approaches that in which agents do share some information in a way. And it's actually true that if you make coordination more explicit, you can improve the collaborative play. Okay, so that's one point. The other point is that reinforcement learning, I mean, some of these reinforcement learning algorithms, like the most basic ones, such as the tabular Q value, is operating on in a Markov decision process. I mean, some of them are, it's not clear whether, you know, you can easily transfer reinforcement learning algorithm to the environment, which is non-stationary. And from the perspective of a single agent, now its effective environment is non-stationary, right? So you'll see also that these non-stationarity issues can have some, can cause some problems. Okay, but independent learning is sometimes useful. And for example, I'm going to show the video where you can sort of obtain emergent cooperation by using independent Q learning that we mentioned in the last lecture. So here what you can see is basically two independent Q learners that are trying to cooperate on Pong game. So here the reward of the game is changed so that agents are incentivized to keep the white ball as long as possible in the game. And the interesting part is that some interesting behaviors emerge. Like, for example, you'll see, I think, soon that one of the players won't even try to serve just to avoid negative payoff. Like, I think at this point. Then at some point, these agents figure out that eventually what you should do as your best strategy is go all the way up on the screen, right? Yeah, like at this point, they will go both on the upper part of the screen, and they're just going to preserve the ball, right? Let's see. Yeah, now they sort of learned that this is the sort of really effective strategy. Okay, so this is nice, but as I mentioned, like, you know, non-stationarity can be an issue, and especially for providing some formal results. So I'm going to maybe briefly talk about this, because sometimes you really do need to have sort of an independent learner. The question is, how do you then design this independent learner so that it accounts for the non-stationarity issues? So as I mentioned before, effective environment of agent 1 is basically environment plus agent 2. And from the perspective of agent 1, rewards and transitions are non-stationary. So now the question is, what happens? I mean, it's not stationary because agent 2 can change and adapt over time. And the reason why we care about you know, designing good learning policies for A1, despite, you know, this changing behavior of A2, is because there are practical scenarios that fit within the setting where the second agent is not in our control, and it changes this policy over time. And one of such settings might be human AI collaboration. Hopefully we'll have time to see the results that actually indicate this. Okay, so yeah, so I mean, why do we care that much about it? Well, because it's not actually easy to deal with non-stationarity from a theoretical point of view. And as we analyzed in one of our papers, it's actually much more computationally challenging to obtain some probable guarantees, even in the setting. I mean, you know, deep learning, it's really hard to analyze, but there are settings where you can analyze these algorithms, such as tabular settings, and obtain some probable guarantees. But when you have non-stationary environments, it becomes much more challenging. So if the second agent is sort of arbitrarily changing its policy, there are cases where it's really hard to deal with that. But if agent 2 is maybe slowly changing, like agent 2 is somehow learning over time, and this is the setting of multi-agent reinforcement learning that we are focusing in this lecture, then there are algorithms that can help you deal with this, right? So, for example, one way of doing this, as we discussed in this paper, would be to basically use OFTRL algorithm that we talked about. But this OFTRL algorithm would define our policy by being deployed to each state separately. It would have its reward function, its effective reward function would be defined through Q values, and would actually not just use one such algorithm per state, but multiple of them. And these multiple algorithms would basically have different history horizons that they would look at, and then the averaging of these outputs of these algorithms would define the policy. Basically, they would define how to act in each state, and since we have for each state design such a system of several OFTR algorithms with different history horizons, would be able to define the policy. So there is basically what I want to say here is that, you know, the multi-agent setting seems in this case to be a little bit easier if you have the other agents learning, not just acting arbitrarily. So this is this has a similar flavor to what we had before in the repeated game setup. Good. Let me see if there are any questions. Okay. Good. So yeah. So however, it's often the case that, you know, we can control the training process of multiple agents. There is no reason why we wouldn't consider centralized training. So if you have multiple agents, what you want to do is design policies for each of them that is dependent only on their, let's say, local observations, which means that we need to somehow factorize this policy into multiple of them. So this can be done by design, right? And that's great. You can do this. Now the only problem is this fact that you can do centralized training, but you also need to account for the fact that we are receiving global reward in this situation, right? So we need to somehow split reward based on contributions that each of these agents make in making the final outcome, basically by contributions that these agents make in making the system effective in the learning. So how do we do that? So one approach that is quite practical is based on difference of rewards, in which case we split this global reward functions among agents in the following way. So what we do here is basically counterfactual reasoning, where we have reward for an agent 1 defined by saying that we are going to try to measure the contribution of agent 1 by seeing how much its own action, A1, change the outcome, change the reward with respect to some baseline action that an agent could have performed, baseline action B1. Notice here that, rewards of each of these agents is dependent on all of the agents' actions, right? So we are keeping that, but we're just trying to counterfactual reason, what would have happened if agents had done something else in the world. What we have here, given by the environment, is reward say, but what we don't have is this counterfactual reward, right? Because agents, what they did in the environment was to take action A, but we didn't receive the counterfactual reward, right? So the problem with this approach is that it requires a simulator, right? It requires us to simulate this counterfactual. However, furthermore, it doesn't also take into account long-term effects, like if an agent takes action A in state S, myopically, this action might be good, but over a long time horizon, it's sort of like not clear whether this is the right way to distribute the payoff. Good. So how do we take care of long-term horizon? Well, we can utilize Q values, right? So one way to do this would be to define the difference reward approach, but now in terms of Q values. And this difference of this difference of Q values is basically effectively defining advantage function. It's called counterfactual advantage function. It's written here by A1. Right. So what do we do here? So we first of all calculate Q value for the joint action A, and then we calculate the Q value for the joint action that doesn't, that sort of somehow integrates out the action of the first agents, first player. And it integrates it out by using a policy of the agent. So basically, this Q value is the expected Q value that the joint action would have if everybody else acted as they are, but agent A1 acted according to policy pi1. Okay, so it's basically resembling difference reward approach, except that here we are this baseline is obtained from the policy pi1, which is in general stochastic. And this really resembles advantage function from the previous lecture. Okay, so this means that we might be able to utilize actor-critic approach, and indeed, this is what Forster et al. Proposed. basically an actor-critic way of dealing with the credit assignment. So in this scenario, our critic would be a centralized critic of Q values, because if you go back to this slide, in order to calculate advantage function for each of the agents, we need a central critic that accounts for all the agent's actions. So we can do this from the data that was obtained by executing the joint policy. So this pi theta here denotes policies of all the agents jointly executed. And then we can utilize, let's say, actor critic approach that updates the parameters theta of agent A1. Agent of all of the agents, so agent 1, agent 2, and agent 3, depending on their advantage functions. Good. Does it work? Well, Forster et al. Analyze this in a setup of StarCraft. In the setup, you basically are trying to micromanage units, 5, 7, depending on I don't remember exactly these hyperparameters, but I think there are actually different setups, different number of units that you are trying to manage. And yeah, the important part here is if you look at this graph, which shows the average win rate in percentage of an agent that is trained, an agent that, cooperative training procedure that is designing, that is outputting these agents policies with respect to against an agent that is an AI agent that is typically used in StarCraft. You can see that cooperative training with comma achieves much better result than independent learning approaches, denoted here by green line. So comma is shown here with this red line, and green lines are showing independent learning approaches. So yeah, just to conclude this part of the lecture, effective training of agents to cooperate is an important, because we have practical scenarios that that are cooperative, decentralized, where we want to have decentralized execution, and there are different ways of achieving this. But there are many challenges, especially algorithmic ones, due to the non-stationarity. So even if you are in a cooperative mode, the presence of other agents are somehow making things challenging. So we discussed two different approaches: independent learning and centralized learning, but you also have approaches that are sort of in between, right? They are trying to utilize best of both worlds. So for example, centralized training is a nice approach, but it requires this centralized critic, and centralized critic, might be, we might be able to do something more efficiently in this decentralized way, right? So this is what some of these approaches are discussing in the literature. Okay, let me just check if there are any questions on Slido. Okay, so finally, let's talk about agents modeling in MAR. So again, we have a, let's say, cooperative setup, or it can also be competitive. But now the goal is, we are going to design agent 1, but this agent 1 sort of has this possibility of modeling other agent, right? So the idea here would be to say, look, can we maybe model the second agent? And with this good modeling, can we try to find a good policy for the first agent based on the best response, or based on some other response model of the second agent, right? So the idea here would be to learn the model of the second agent so that we can use it in multi-agent interaction. And yeah, this is, this approach is also what humans are using. And there's this famous theory of minds. which is saying that humans also build mental models of other people. They build models of agents' beliefs, of their intents, desires, and so on. And we act on it. Even children do this. Children from age 3 to 6, they also build models of other people. So they do recognize that other people are different, and they differ by their beliefs, intents, and desires, and so on. So why not do something similar for the machine learning setup? And this setup of theory of mind has also been proposed actually for reinforcement learning framework. And the argument here is really, we might need in different applications a model of other actors in the world in order to act appropriately, right? For example, if you take a look at the abstract of this paper, it's going to say that, some model of the other agents in the world is an important step forward for developing multi-agent AI systems. And in particular, the interesting part is that they are also saying here is that it's important for human-machine interaction, right? The reason for this is because, you need to interact with an agent that you're not actually controlling. Good. So, yeah, this brings me to the project that I mentioned at the beginning of the first part of the lecture, this helper AI notion, where you have assistive AI assistant, right, that is interacting with the other agents, which would be human. But the goal here would be to say, you are somehow developing an agent that accounts for the fact that its human collaborator might have different behavioral aspects. Behavioral aspects meaning that it can have, for example, different views on how the world works. Good. So, you might be thinking, okay, why would this be important? So let me maybe show you a short video clip which demonstrates that there might be situations in which, if, let's say, this AI system doesn't account for the behavior of other agents, the system might perform, the overall system, the joint overall system that contains both AIs and humans, might perform relatively poorly because of, let's say, misaligned views on how the world works. So humans might have some, let's say, behavioral biases and might override the system, even though the system would be safe and perform maybe optimally with respect to some objective point of view, right? So I'm showing here a self-driving car as one of the prime examples of human AI collaboration in the long-term decision making. Yeah, so basically here we have a human who stopped the car. Even if the car would have stopped, the human behavioral biases kicked in, right? So how do we model this situation? So we can use models similar to stochastic games, two-agent Markov decision process, but now this model has a slight twist to a standard setup of stochastic or Markov games. So in this case, agents align in the reward that they obtain, but they have misalignment in how the world works. And this misalignment is represented by two agents. In the case of human AI collaboration or this helper AI system, we would have two agents. One is helper AI and the other one is human. these two agents would have different probability, transition probability. They would think that the world acts according to different probability transition matrices. There's probability transition kernels, right? So basically here, for example, for state 0, they would agree that taking the same action leaves them in state 0, which gives them 0.5 reward. But they would disagree on what happens when they have misaligned actions. So if they take different actions, this helper AI would believe that it leads them to state S1, whereas human, which is worse than original state, and human would believe that it takes them to state S2. Okay, so this misalignment creates actually game theoretic challenges in this model. And of course, you can provide some theoretical characterization by using such a modeling approach. I mean, typical result that you can show is that, naive way of approaching the design of these helper AI tools will actually lead you to lower joint utility, a lower cooperative utility than what you would have if you do model human somehow and incorporate this model in the design of helper AI agent. And this in turn is lower than the optimal utility that one can obtain when both agents are have aligned views on how the world works. So they have both correct transition kernel matrices, transition kernels. And of course, you can also quantify the gaps between these utilities. But I'm just sort of showing you something standard result. That's, I mean, it obviously we can improve upon this in specific situation. But this is just sort of just something that I mean holds based on modeling assumptions. And if you remember that car driving scenario that I mentioned in the first lecture, well, you can sort of think of this as a two-agent system if you allow humans to intervene. So we actually try to see what happens if you have artificial human, right? A driver that would intervene on a self-driving car, but this artificial human wouldn't have a correct transition probabilities. And it appears to be the case that often it's not just that, it's not just that naive modeling of when you don't account for human is worse than when you account for human. So when you do incorporate some model of a human in the design, it's also often worse than just letting human drive the car, right? Yeah. So this was sort of a planning setup, right? Everything was known about the world. Helper AI agent knew what transition probabilities are, so you could just perform planning on top of it. But we actually tried to do to place this framework also in the reinforcement learning setup on Atari games. Here you see collaborative form of Atari two-player games where we sort of tweaked some of these. Basically, we shape the rewards so that the game itself becomes collaborative. So the question is, okay, how do you then? I mean, in the planning procedure, it's sort of if you have a model of a human, then you can design a good planner. Now the question is, what do you do when you're in the reinforcement learner setup? Well, first of all, you could try to directly learn these helper AIs by putting human in the loop, but this is often not practical, right? Because humans would need to play a large number of games with these helper AIs. So the idea would be to then replace human with faithful imitation of a human, right? So you need to somehow construct this imitation learning algorithm. Sorry, this imitator of a human that would then interact and be used to train helper AIs to play well in collaborative setting when they're interacting with the human, right? So the point here is basically to somehow avoid having human in the loop, basically, when training helper AIs. But when you're executing them, then you are of course executing them in the collaboration alongside with human. So we actually tried to experiment a little bit. Paul Tilkin was doing these experiments together with my other collaborator, David Parks. And I mean, in the simplest case, this is still an ongoing work, but in the simplest case, you can design, for example, imitators that just match human performance, right? You can train these imitators. One way to train them is in the self-play mode. And then you can have different levels of sophistication of these imitator agents. And now the question is, okay, what happens when you put these imitators in two different cases? In the first case, when you put them with an imitator that has higher sophistication level when it's playing in the self-play, what happens is that this higher sophistication level doesn't actually necessarily lead you to better results. It can actually hurt you. So collaboration of higher level imitator agents with a lower level imitator agent can actually be worse than what you obtain with two lower level imitator agents that are trained in the self-play. Then you can also ask what happens if you actually train a helper AI to collaborate well with these imitator agents. You can, of course, increase the performance because these helper AIs are aware of the second agent. So the point here is that even though these level 4 agents, when they're trained in the self-play, are performing well when collaborating with themselves, they're actually performing relatively poorly when collaborating with imitators of lower levels. So some robustness needs to be imposed here when designing collaborative agents. Of course, you might ask, does this actually happen in practice? And actually, the results of Carroll et al. Suggest that it does. So what they did was effectively an experiment where they actually use imitator agents obtained through imitation learning algorithms that we discussed in the first lecture. So basically, they collected a bunch of plays from humans. They utilized behavior cloning, obtained good imitator agents. Imitator agents that were imitating human play, and then they basically assessed the same similar characteristics to what we've seen before, and obtained qualitatively similar results. So it really seems that these models of humans, when we are talking about human-AI collaboration, they seem to be important. Yeah, so by the way, the additional insights that I have is that if you're talking about some future directions, that first of all, better models of human behavior might be useful for this design. So imitation learning algorithms are not always, it seems to be that the existing imitation learning algorithms could be improved in this respect. Furthermore, adapting to humans also seems to be something that might be relevant. So, at some point, these assistive agents or collaborative AI agents might need to interact with a wide variety of humans, and you want to be able to interact with all of them. So basically, at execution time, you want them to be able to quickly adapt to the human that they are interacting with. And finally, there's also shown the experimental results also indicate that humans are also learning while they're interacting. So humans themselves are non-stationary, which is what I mentioned in the second part of the lecture. So, you know, there is, you need to account for this when you're designing algorithms that are going to collaborate with humans. Yeah, so of course, this is not the entire story of agents modeling in multi-agent reinforcement learning. We just discussed one aspect, but there are also other aspects that are relevant for cooperative and competitive agents. Here we discussed cooperative case mostly. And in this case, we were considering, you know, whether we can derive from the data models of other agents, in this case, humans, that could be utilized by collaborative AI agents. Of course, one can also try to use approaches such as machine theory of mind, where, you know, you want to quickly adapt to your collaborators. So in this paper, machine theory of mind, the goal would be that you somehow learn to predict how the agent would behave just from a limited amount of interaction with that agent. So that's an interesting, but there are also other aspects in multi-agent reinforcement learning when it comes to agent modeling. Like, for example, we might want to learn to, we might also want to have models of learning of other agents in order to create good learning procedures for agents that are learning themselves. There are also a bunch of other aspects on autonomous agents modeling of other agents, generally multi-agent systems, not just multi-agent reinforcement learning. So furthermore, there are also many other aspects of multi-agent reinforcement learning that we haven't mentioned here. I haven't focused that much on more complex games, such as the ones that were mentioned in the previous lecture by some of you. Second of all, we haven't even touched on multi-agent reinforcement learning in like social dilemmas. So these aspects, I also find them interesting, or for some kind of multi-agent RL for social planners. We haven't talked that much about, we haven't talked at all about communication protocols, or whether you can learn it directly by utilizing reinforcement learning. And there's also an interesting aspect of how do you actually evaluate agents in some of these, let's say, competitive scenarios. So as I mentioned in one of the slides, you know, you can have self-play working well for transitive games. If the game is non-transitive, then the question is whether self-play is a proper procedure. I mean, you need to tweak it or tweak this way of reasoning if you want to obtain useful results. This is what, anyway, some of these more advanced papers are doing. But you know, non-transitivity games also imposes the question of how do you then evaluate agents if you don't have any transitivity. So there are actually quite some interesting papers that are discussing this in that context. So just to summarize, in this lecture we discussed Markov games as a formal model of multi-agent reinforcement learning interaction. The topics that we covered were related to competitive multi-agent reinforcement learning, cooperative multi-agent reinforcement learning, and agents modeling. And I mean, this lecture was created by using a bunch of references that I list here. I think in regards to Introduction to Multi-Agent Systems, I would definitely recommend this book by Shoham and Leighton Brown on multi-agent systems. And several survey papers on multi-agent reinforcement learning. So thank you very much. And with this, I think we are ready to to take questions. Let me see if there are any questions at the moment. Okay, at the moment. Oh, we only have the question from the previous lecture on transfer learning. Well, I guess I can maybe reiterate this. Yeah, in transfer learning, I mean, you can transfer knowledge from one agent to another in different ways. One of them is this imitation learning approach that I was talking about. So you can have sort of one agent trying to imitate the behavior of other agent to design good, maybe prior policies. Yeah, so maybe that's one way of doing things. Or you can also try to do this in the case of meta-learning, meta-reinforcement learning. One can design good policies and then good prior policies, these pi theta policies, and then basically optimize for specific goals that agents could have. There are also other approaches, I mean, in reinforcement learning that we haven't talked about, that people have started to investigate in relative recent years, such as combinations of unsupervised learning with reinforcement learning, where, for example, an agent is trying to sort of achieve many different goals in initial phases just to discover what I mean, the goals are maybe not predefined immediately, right? So you sort of put an agent to try to reach different possible goals, and by doing this, the agent sort of learns more about the world. Okay. Yeah, meta-learning, I haven't said anything about this, but meta-learning, meta-reinforcement learning is also something that might be interesting, and might be interesting also in this context of human-AI collaboration. Yeah, so that would be about it from me. And thanks everybody for being a part of this lecture. I really enjoyed.
Okay. Thank you really very much for this interesting lecture. Thank you.
Thanks.